Our pleasure and honor to me to warmly welcome distinguished guests and speakers, Head of Research Organization for Electronics and Informatics BRIN, Professor Dr. Engineering Budi Prawara, Head of Research Center for Electronics BRIN, Professor Yusuf Nur Wijayanto, President of Indonesian Solar Energy Research Society, Professor Natalita Maulani Nursam, our keynote speakers, Professor Dr. Fenadi Swendo from Institut Teknologi Bandung, Indonesia, Professor Mingqi Wen from Huazhong University of Science and Technology, China, Professor Akihiko Fuji from Osaka Institute of Technology, Japan, Dr. Vipindraj Sugatan from Nanyang Technological University, Singapore, Professor Luigi Fessi from University of Rome, Tor Vergata, Italy, Dr. Juliar Firdaus from BRIN, Indonesia, Professor Zipeng Kan from Guangxi University, China, Associate Professor Gyo Min Kim from Hangkyong National University, South Korea, Dr. Muhammad Naufal Lintang Pradipto from University of Stuttgart, Germany. Our session chairs, Professor Natalita Maulani Nursam, Dr. Adita Asma Nurunizar, Dr. Bening Tirta Muhammad, Dr. Widya Budiawan, Dr. Wilman Septina, Dr. Nunik Nurhayati, and all the participants of the symposium. Welcome to the second symposium on Advanced Photovoltaic 2025 with the theme Recent Progress and Challenges for Next Generation Photovoltaic Technologies, brought to you by the Research Center for Electronics BRIN in collaboration with Indonesian Solar Energy Research Society. My name is Nurfia Uniati and I'll be your MC for these 2 days. To open the event, we will have event report and welcoming speech from Chairman of the committee, Dr. Maria Ulfa. To Dr. Maria, the screen is yours.
Thank you, Ms. Pia. Assalamualaikum warahmatullahi wabarakatuh. Good morning, distinguished guests, Head of the Research Organization for Electronics and Informatics, BRIN, Professor Budi Prawara, Head of the Research Center for Electronics, Professor Yusuf Nur Wijayanto, President of Indonesian Solar Energy Research Society, Professor Natalita Maulani Nursam, dear colleagues and participants, it is my great pleasure to welcome you to the second symposium on Advanced Photovoltaic 2025. This year's theme, Recent Progress and Challenges for Next Generation Photovoltaic Technologies, reflects both the advances we have achieved and the challenges that lie ahead. With more than 400 registered participants, it is clear that our community is strongly committed to advancing solar energy research and innovation. The participants are not only from Indonesia, but also from abroad, like Malaysia, Japan, and United Kingdom. We are honored to host speakers from Indonesia, Italy, South Korea, Singapore, Japan, China, and Germany, covering topics from organic and perovskite solar cells, from single crystal perovskite and hybrid perovskite, and the transition from lab studies to large-scale application. This diversity of expertise promises engaging discussion and fresh perspective. In addition, we are pleased to welcome 8 young scientists who will share their latest work on solar cells. As chair, I would like to thank the organizing committee, our speakers, and all of you for your participation. This symposium is not only about presentation, but also about exchanging ideas, building collaborations, and finding new inspiration. I wish you all a productive and inspiring symposium. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Maria. And next, we will hear the welcoming speech from the President of Indonesian Solar Energy Research Society, Professor Natalita Maulani Nusam. To Prof. Natalita, the screen is yours.
Thank you, and good morning, dear distinguished guests, colleagues, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera. It is my great honor and privilege to greet you all here today at the second supporting this event, which is a reflection that PV technology, green energy technologies, that still attracts a lot of interest. I'm here as the president of the Indonesian Solar Energy Research Society, or ISERS. Would like to take this opportunity to briefly introduce you to who we are. ISERS was initiated during the first advanced and also prior to the event. We captured a lot of interest among the Indonesian solar cell researchers regarding the need to form a community that focus on the research aspect of solar energy. It has then motivated us to form our current society, ISERS. We are more than just a group. ISERS is a space where people come together to connect, collaborate, and grow. Our vision is simple. That is to create a community of Indonesian researchers who reside both locally and globally to foster innovations in solar energy research. We believe that by bringing together diverse individuals and institutions, we can build something truly meaningful, especially to leverage the competitiveness of solar energy technology. This simply serves as a platform of knowledge exchange and research updates. We do is to see you again in 2027, hopefully for the third Advanced PV Symposium, among other activities such as webinars, workshops, and so on, which are also planned to be launched soon. Finally, I would like to invite you all to join our community ISERS. We do hope that ISERS will continue to grow and to serve as an impactful platform in contributing to the development of solar energy research in Indonesia in particular. Again, thank you very much to the organizing committees, to all speakers, and to everyone. I wish all the very best for this symposium. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. To officially opening this symposium, we invite head of the research organization for electronics and informatics engineering Budi Prawara to deliver the opening remarks. To Professor Dr. Engineering, the screen is yours.
Yeah, thank you. Distinguished guests, esteemed colleagues, respected speakers and participants, very good morning to all of you. Best wishes to all of us, and may we all be blessed with good health. On behalf of the Research Organization for Electronics and Informatics, it is my great honor to welcome you all to the second symposium on Advanced Photovoltaics 2025 with the theme Reason, Progress, and Challenge for Next Generation Photovoltaics Technologies. A symposium such as this is more than an academic forum. It is a platform where new findings are presented, where knowledge is exchanged across disciplines, and where collaboration are formed to address global challenges. It also provides an opportunity for established experts to share their insight and for young researchers to engage in meaningful dialogue that can shape the future of this field. In particular, I hope this symposium will contribute to accelerating the growth of renewable energy especially solar cell development here in Indonesia. Allow me also to briefly highlight our research activity at Research Organization for Electronic and Informatics, particularly at Research Center for Electronics, and the research group Advanced Photovoltaics and Functional Electronic Devices. Recently, we have been focusing on the scale-up of emerging photovoltaics technologies, including dye-synthesized solar cells, perovskite solar cells, and organic solar cells. Looking ahead, we are committed to advancing these technologies toward larger-scale module development and exploring their integration with other functional electronic devices. To support this, our center is equipped with facilities for solar cell device processing, comprehensive device characterizations, and clean room laboratories, enabling us to conduct high-quality fabrication and testing under controlled conditions. Together, these facilities allow us to bridge fundamental research with practical applications. BRIN also facilitates a research mobility scheme for all levels, from student to professors, through research assistant and visiting professor or visiting researcher scheme. This scheme is expected to increase human resource capacity and open up opportunities for the research collaborations. We also collaborate with universities for degree by research program, both locally and globally. I would like to take this opportunity to express my sincere appreciations to the organizing committee for their dedication and hard work, to our invited speaker for generously sharing their expertise, and to all participants for contributing their time and commitment. Your presence here gives true value to this forum. With these remarks, it is my privilege and great pleasure to officially declare the second Symposium on Advanced Photovoltaics 2025 open. I wish you all a productive, engaging, and inspiring symposium, and may the ideas shared here today bring us closer to realizing a cleaner, brighter, and more sustainable energy future. Thank you very much.
Okay, thank you very much, Prof. Budi Prawara, for the inspiring remarks. Ladies and gentlemen, before we begin our first agenda, we will do a screen capturing session. Everyone, please turn on your camera for a virtual group photo. To Pak Widya, please lead the session.
Okay, good morning, everyone. Now we have photo session. So open your camera and give your best smile for this moment. I have three slides here. So start with the first slide. 1, 2, 3. Okay, next slide. 1, 2, 3. And the last slide. 1, 2, 3. Okay, thank you. That's all for photo session, and turn to Miss Fia. Thank you very much.
Thank you, Pak Widya. Now we move on to the highlight of today's event. Before that, let us kindly check the symposium rules. Please ensure that your microphone is muted during the session. We will have a Q&A session at the end of the presentation. Kindly use the Q&A feature or the chat box. Feel free to use the reaction icons to show your appreciation for the speakers. Ladies and gentlemen, our first session will begin. This session will be chaired by Professor Natalita Maulani Nursam. The speaker is Professor Dr. Fenadi Swendo. To Prof. Natalita, the screen is yours.
Okay, thank you very much, Ms. Pia. Before I start, I would like to introduce myself. My name is Natalita, and I'm a researcher from the Research Center for Electronics, National Research and Innovation Agency of Indonesia, or BRIN. And today I will be the moderator for this session. So in this very first session of this symposium, we will have a distinguished speaker from Institut Teknologi Bandung, Professor Fenardi Swendo. And before we start to listen to his talk, I would like to briefly introduce Professor Fenardi Swendo. So Professor Fenardi obtained his bachelor degree in chemistry from Institut Teknologi Bandung, Indonesia in 1998. And then he got his master's degree in materials engineering from Tokyo Institute of Technology, Japan in 2001. He obtained his PhD in physics, particularly in thin film semiconductors from École Polytechnique in France back in 2005. He is currently a full professor at the Faculty of Mathematics and Natural Sciences in Institut Teknologi Bandung in the Inorganic and Physical Chemistry area, and he is also a director of the Center for Nanoscience and Nanotechnology Research in the same institute. His research interests include molecular spectroscopy and also semiconductor materials. Welcome, Professor Fenardi. Good morning.
Good morning, Bu Natalita. Thank you very much for the kind introductions.
Thank you, Prof. Fei,
It's a
for
great pleasure to be here.
Yes, thank you very much, Professor Fenardi, for joining us today, this morning. Maybe before we start, I would like to remind you that in this session, you will have around 30 to 40 minutes maximum of presentation. And perhaps you would like to share your screen?
Okay, yes, please.
Thank you again, and we look forward to listening to your talk. And the screen is yours. Please, Professor Fei.
Thank you, Professor Natalita. It is a great honor to participate in the second symposium on advanced photovoltaic. Personally, I thank the organizing committee for the chance to share our idea and experience with others in the symposium. Actually, I will not say that it is something great for the talks, but I want to revisit about the fundamental of the PV technologies, PV and science, and the science of PV, also its technologies to fabricate the PV cells. Actually, I want to revisit the interfaces. So I entitle my presentation Interfaces, the Main Challenges in PV Fabrication and Material Designs. Here, actually, of course, we'll open that why we are Indonesian really eager to develop the PV technologies in our countries, because our countries located in equators. So we have a really great potentials to have a whole year's sunlight. So that means if we can install many PVs, that means we will gain many benefits. And then, as we know that the commonly used PV cells nowadays is based on the polycrystalline silicons. And if we compare with the spectrum of the sun, that means we cannot cover all. So that means that we have to either develop other materials or make a tandem system or something. But before go further, maybe we can revisit or recall back about how we can harnessing or harvesting the sunlight. We use, we can say that PN junction type devices to extract the photo-excited electron or photo-excited electron and hole pair to the external circuits. So that means that if we want to have a more voltage or more current, that we can just put in series or in parallel, so we can get the modules which can fulfill our requirement or our needs. But it means that we have a lot of interface in that case. And then many, if we recall back about the solar spectrum, maybe not all the solar spectrum covered with the silicon. So many researchers around the world, around the globe, they try to develop many type of materials with different efficiencies, different spectral response, etc. But we can see that the trends of the development of the PV cells will go to the tandem system. So that means that, of course, we increase the efficiencies, but in some part, but also we decrease in some part the efficiencies due to the interfaces. So that means that if we play with tandem system, or we develop new materials in PV, that we always face problems in interfaces. If we return back to the photovoltaic effect, maybe we remember clearly that we generate voltage and electric current due to the sunlight, and how it can be obtained actually with analogy of the photoelectric effect. But the difference is one in vacuum, one inside the device. We have a separation of the charge. And the separation of the charge in this material, we have to harness, we have to bring them outside the device to the external circuit. In this case, we need a built-in potential or internal electric field that we only can get it if we have like a PN junction type of the interface or device. If written back to the basics, first maybe for the silicon system as the first type or the first generation of the solar cells, we have intrinsic type of silicons, and then if we dope with boron, we can have a p-type of silicons, and then if we dope with phosphor, we can have n-type silicon, and then we combine this interface. Actually, it's not very easy to combine this interface. So long time ago, they called metallurgical junctions or metallurgical, how to say it, interfaces. In this case, that we try to, people try to develop this kind of interface and form such kinds of PN junctions. So we can have a space charge region here, and then we have built-in potential. So we have electric field that force electron to the n-type or n-dop parts, and then the whole will be forced by the electric field to the p-type dop or the p-types. And then in this case, we can harness the excited or the photo-excited charge carrier pair, the electron and the electron hole pair. But nowadays, that the of this idea we develop with or we try to generalize this type of the device, not only exactly the PN junction, but we try to become a more complex system. Maybe we can say the DSSC or the others, not exactly PN junction, but we still have the idea. And then if we go to the function of the PN junction, we can use at electron hole pair recombination and also electron pair generation. For the electron pair recombination, we can use as a device for electroluminescence, LED, diode laser, etc. So, but on the other hand, for the photovoltaic, we need electron hole pair generations. So that means that we need the interface between P and type material generate so many photoexcited electrons here. So with this idea, people try to move around and then to develop the PIN type junction. What we can say that it is become more feasible in different type of silicon. For example, the amorphous type amorphous silicon or microcrystalline PV. So if we can summarize the evolution of the spectral region in PV, we can say that people start with metallurgical junction forming electronic junction for the PN junctions. And then when they realize that they need a clean materials that generate the electron hole pair, so they try to insert intrinsic type between PN type layers. So we have the PIN junctions. And in this case, they tried also to make the I-type layers become thicker and thicker. So they get the most efficient system or combination between the thickness between P layer, I layer, and N layers. So, but when we go further to different type of or different materials of the PV or solar cell, or we can say that we try to expand or generalize this electronic junction, we can go to the concept of HTL active layer and ETL junctions. Or it's more common in perovskite solar cell, for example, in plastic solar cell or organic solar cells. But for the DSSC, they develop for counter electrode redox couples, die, and ETL junction. It actually is a quite complex one. So we can say that in third generation solar cells, we can have a many type of the junction, can be solid liquid junction, molecular liquid junction, molecular junction, semiconductor molecular junction, and etc. to forming electronic junctions. So we in the end, many researchers try to how to say, this type of the junction that can harness the solar energy, it can be expanded, can be generalized. So as long as they have like a built-in potential type of the potential, we still can harness the electron hole pair generated by the photons. But the problem is, if we go back to the classic mathematical junction, the quality of the junction is very important. So that means that how the space charge region can be formed, and then they have a good built-in potential. That means in the end we have a good VOC. We have to have a good interface. So long time ago, normally they play with thermal. So they try to make a P-type. Start with the P-type wafer, for example. They dope with N-type, and then they have a good junction. If not, they will go for annealing, etc., to improve the interface. So that's their approach. But when we go for the solid liquid junction or other type of the soft interface, the approach will be different. We cannot play with thermal, but maybe we have to play with some preparation before applying other layers. For the solid junction, normally they have three types: type 0, type 1, and type 2. The semiconductor liquid junction, the type 0. And then the metal insulator junction is type 1. And then the type 2, we have buried P plus N junctions. Actually, this solid junction also we face in many type of the devices, especially photoelectrochemicals such as DSSC. And nowadays also people start to develop some molecular junction. They put the molecules make an interface between the electrodes, or even the interface between molecule and molecule, the molecule sandwich between metal, etc. Also, this type of junction is a new type of junction that we can say that kind of the soft type of the molecule of the electronic junction. So that means maybe we can harness quite efficiently the photon, but the problem that maybe it cannot withstand for a long period of time. But the advantages because it is a soft junctions, so maybe we can repair. Meanwhile, we can use this device. And then for the molecular liquid also they develop, because they think that we can have the interface between semiconductor and liquid. Maybe we can also put the molecules on the top of metal and then have interface with liquid. So we have the photoelectrochemical system, but with molecular junction. They tried also this type of junction, and we can say that people modify so much for this liquid junction and many new junctions. But still, in application, the traditional one is still cover the market, I believe, because nowadays still polycrystalline or tandem with the amorphous silicon or microcrystalline silicon still become the working horse for the cheap PV or commercial PV, because for here that for the PIN junction normally used in amorphous silicon, hydrogenated amorphous silicon, and hydrogenated precaution silicon solar cells, we can have two type of configuration, either PIN or NIP. It depend on our reactor or our deposition system, and also with our goals normally, because in many system normally we cannot easily deposit the TCO, for example. So we try to buy the TCO glass, and then we just deposit the PIN. So normally for the larger laboratory, they can prepare their own TCO. They have spattering, they have a soft sputtering deposition, for example. They can have a metal substrate or metal on the glass, and they deposit NIP, and they close with the TCO layer. They deposit the TCO layer, and they can have the NIP configurations. So it's depend on. But one thing that we have to consider that for each layer, we have to prepare carefully, and then they have their own interface problem. So when we have the PN junction, we only have, of course, we have substrate, for example, TCO substrate, and then so we can have the junction between the TCO and P-type, for example, or if we start directly from the crystalline silicon, maybe we will have, how to say it, PN junction itself, and then we have the metal back contact, and then we have the TCO with sputter on the top. So at least we only have three interface. But for the case of the PIN junction, we add another. We have additional one interface. So we add some additional problems. So when we have a more complex system, maybe we can think that with my tandem, we add the more layer, we can gain the absorption of the light. But the problems that we add more and more how to say it, the interface, and then that means that the charge carrier that we generate from the photo excitation has to flow through that interface also. So when the interface is not good, that means that we will reduce the efficiency of our cells. And when we go to the decentralized solar cell, I think it's quite popular in Indonesia. Even I start my PV career in Indonesia, starting from this type of solar cells. Actually, it's very easy to establish because no need so many advanced equipment. But the problem is that actually, my personal opinion, we have two problems, because the first problem is it has a lot of interface. For example, we can imagine here we have the because we deposited normally the platinum itself on the top of the FTO glass, for example, we have the interface between the FTO and the platinum or the other electrocatalyst, and then between electrocatalyst and the electrolyte we also have interface, and then the electrolyte tends to evaporate, so maybe we can go to the quasi solid electrolyte. But the problem is that the interface is not as easily controlled compared to the solid liquid interface, because quasi solid sometimes they will not wet our electrocatalyst. And then also in the other part with the interface between molecules in our host semiconductor, in this case maybe titania nanoparticles. And then from titania nanoparticles, we have also the interface with FTO. So many interface, and then that makes the in one side the SSE have some limitation, and also how the redox couple diffuse to regenerate the dye also gives some limitations in the current. So actually, we still have to work a lot for the DSSC to overcome other type of the solar cell, especially the emerging one like perovskite, because so many groups start to leave behind the DSSC. But actually, in some sense, especially when we start to study solar cell, we can say that the idea of the space charge region in the SSC is really clever, because we don't have a real PN type junction here. Even we have a very thick cells compared to other type of the solar cells, but we can still that there is a space charge region here. Actually, between the interface of the electrolyte and the dye molecules, and the semiconductor and the host semiconductor. If we go to the organocolloid perovskite, actually it is now become new emerging topics. So many groups work in these topics. But the problems when we go for the, for example, solution-based deposition system, maybe our other colleagues there will be talk about that, but also some people works with vapor deposition routes. It is, in one sense, it's better. In other sense, there are also some limitations. But from the interface problems that and also the compatibilities between each layer, when we work with the solution-based perovskite solar cells, is actually quite tricky, and we need to have a good strategy, because at least we have only two configuration here: the N-type or normal setup, or P-type inverted planar setup for the perovskite solar cells. But sometimes if we try to make the cells better, not all the component is compatible. So normally what we got in published papers is already compatible collections of the materials. For example, for the N-type, we'll have FTO, and then we deposit the titanium compact layers, and then we have nano titania, and then we put the perovskite capping layers, and then we put HTL, and then we try to choose the best HTL according to the band alignment, etc. And then we put the back contact layer. So we can have the N-type one or the normal setup. But if we have some problems for our material, for example, we can go for another strategy. We can have the ITO glass, and then we can deposit. We can set ETL or HTL PSS in this case, and then we put the planar perovskite layer, and we put the ETL, and then put another back contact layers. So we can move around, try to deposit which one first, and another the second one, another one the third layer. So actually, not each layer have this same compatibility according to our methods. So actually, the solution base is quite challenging. So if we have a good or a lot of collections of materials, or a lot of collections of even the HTL, ETL, or type of the perovskite, and also all kind of solvents, anti-solvent, etc. Maybe we can choose the best. We can modify it to get the best strategy to deposit our layer, because using the solution base actually not as easy as in vapor deposition system, because in vapor, if we deposit A before B or B before A, is not much difference. But for the solution is very different. Is very different, because sometimes if we deposit A and the solvent for the layer B will deteriorate the A layer, so that means that you cannot have a B a good interface. And then maybe you have to start with B, because the solvent of A will not deteriorate the B layer, so we'll have a good interface between B and A layer. So that means we cannot do the reverse. So for the solution base, the sequence, this deposition strategies, and also how we manage or some preparation to manage, we have a good surface and interface. Surface before the deposition, the interface after the deposition, another layer, is become very, very important. And then sometimes we do such kind of routine, how to say, only based on the experience, without some real strategy to overcome these problems. Nowadays is already, so far, people already published about collection of ATL and perovskite active layer and HCl so far. And also some TCO, we have the FTO, ITO, and some group they try to use a new one like graphene or carbon nanotube. They disperse in some, how to say it, transparent polymer, etc. But still we use the FTO and ITO as the how to say, state of the art for the TCO. But for the ATL, we said already a lot of, and then which is for example, like titania, zinc oxide, tin oxide, they have more or less the same, similar, and niobium is slightly different. We have also PCBM for the organic one, and then for the perovskite, they have a different type or different band gap, and then different band alignment. And for the HDL, also we have several different organic and inorganic collection. We have NEOX, we have copper thiocyanide, P.PSS, P3HD, SFPTAA, etc. But we can say that if we differentiate this collection of the material into two groups, maybe we can say that we have organic and inorganics. Of course, for the perovskite itself, there are hybrid organic inorganics, but for the ETL and HTL, we can say that we can separate into two groups, organic and inorganic. In some cases, the inorganics is tough, is stable, but the problem is that it's not really flexible to deposit inorganics. Of course, we can use we can have the precursor and then we can deposit with spin coating. We can also deposit them in some cases with electrodepositions. But you know, this method sometimes is not really flexible. So for inorganic, normally we deposit first. But for the organic, it's very flexible. You can use solvent, deposit them with spin coating, with spray coating, with dye slot, etc. But the problem is that they're not as tough as the inorganic. So we still have to play with that. And then when we have the interface, we have to be sure that we prepare the surface, the clean surface before deposit another layer. So we have a gut interface. So here, what I want to share the idea that it is very good if many groups exchange their data about their collection of the materials, either the active layer itself or ATL, HTL, including their method, how to apply it, and forming a good thin film. And then, of course, when we have a standalone thin film on the top of the glass or top of the Corning glass or on top of the FTO or ITO glass, actually it's okay. But when we want to start the second layer or when we want to apply this technique, deposition technique on the top of our, for example, active layer, for example, perovskite or other organic active layer, for example, it is a challenge actually. We have to be sure that this method, including solvent, including the deposition technique, including the maybe if we go to the vapor or gas or vacuum technique, including the energy kinetics, it will not deteriorate the layer that we deposit before. So many considerations. So that means that if we have a collection of material, we have even for the same material, but we have a collection of method how to apply it, how to deposit to form a thin layer, it is become very good and very important. For example, for depositing autosynthesizing organohalide perovskite solar cell, we have different common published method. For example, two-step solution method, one-step solution deposition, sequential deposition method, and then vapor-assisted solution deposition, for example, and dual source vapor deposition. In this case, I think the most flexible one is the vapor deposition system compared to other. Of course, the problem is that you have to spend a lot for the equipment, but still, if we collaborate among the network, as presented by Professor Natalita, that maybe the group have their own technique, the group they have own develop their own knowledge about how to deposit their own materials, and then maybe for the same material they develop several techniques. I think is very important, and maybe we can exchange and maybe we can share the problems or between us, and then maybe something easy for other groups maybe is a big question mark for other groups. So if we collaborate together, that will be very, very good. And then for the thermal vapor deposition method, because actually a long time ago I worked with the amorphous silicon, polymorphous silicon, microcrystalline silicon. So I always work with the vacuum and the gas system, vapor or vacuum system. So the thermal vapor deposition method actually what we consider a technology with quite reproducible and how to say controllable, etc. So some advanced technology actually. So here I can mention some advantages, including high uniformity and reproducibility, high compatibility with existing technology, and produce high efficiency cell. And then it's quite how to say it's very reproducible and also versatile and interchangeable layer by layer deposition. That means if you want to deposit A first before B, or you want to make a sequence, or we want to alternate A, B, or BA, it's possible, and then it's and the thickness is controllable, so it's very easy. And then also they don't use any toxic solvent, so it's advantageous. But the advantages is that it's the complexity of the equipment and high investment is also become some consideration. So in Indonesia, the thermal vapor deposition method is not how said is quite rare. I don't know if the industry they already have this kind of equipment, but in ITB or in some of our collaborators, they don't have. Still, we struggle with the solution based method. And then because using the vapor deposition method, normally we have a material loss or low material utilization, and also some scalability changes. Because, for example, if you design the reactor for the 10 by 10 wafer or 10 by 10, for example, one to make like a tandem silicon peroxide solar cell, is we design for 10 to 10 wafer. It's difficult to have if we want to end immediately upscaling the system, for example, for 20 by 20, or maybe already designed by 20 by 20, but it's not easy to make the system possible to upscale to 30 by 30. So the reactor design since the beginning for certain size, and then also in some case it is also some complexity for precursor management. So sometimes we have to design the precursor very good to be evaporate using this method. And also if we don't really adjust the deposition condition, we will have some problem for non-stoichiometric surface layers. Okay, I think in the second part of our presentation, I will try to explain about what we already developed in our laboratory. Actually, in the beginning, my collaboration with my friends, now he become minister, is they asked me to concentrate for the DSSC, but only one part. So in most of my career, I already developed for HDL or counter electrode for DSSC, especially the platinum-free based on the polyaniline. So we develop based on the polyaniline, and it can increase in some quite interesting way the efficiency of the DSSC. And then we also try to they have a nanostructures using the soft plating. And then also we try also some different strategy to become they have like a spiky structures like a durian for our polyaniline. And then we combine also with graphite, combine also with RGO. We also increase the efficiency of our cells. And then so in many years, we stick our research only in PT-free based on polyaniline for the counter electrode for the DSSC. And then because we also develop the RGO based on hammers, etc., we also develop another type of RGO combined with polyaniline based on electrochemical exfoliated graphene, EEG. This also give a good results. And then because the processability of the polyaniline still become problems, we also try to make it become a soluble. So we try to put another functional group inside the polyaniline, so because we can put the sulfonated negatively charged group there. So it can be solved. It can be dissolved in methanol, ethanol, and waters. So it's become processable for the polyaniline if we put the sulfonic group there. And then when it becomes soluble, actually, we can also make it become more feasible to deposit on any other surface. And we also make a new type of the material become one of our collections. And then actually we have just accepted article related to this material when we combine the sulfonated polyaniline with the polyaniline to become acid-bare paste. And as acid-bare paste, this it might be similar to pellet PSS, because pellet PSS they have like negatively charged PSS, and then it's doped and the doped positively charged of P dot, and this acid-base pair we try to mimic using the sulfonated polyaniline with the polyaniline itself.
Excuse
And
me,
then,
Prof.
oh yes,
You have 1 more minute.
okay, thank you. Thank you, Bu Natalita, to remind me. And then I think the other one is we have polymerization polyaniline deposition using the electrochemical depositions, and also the electrochemically extruded graphene. Also, we produce in our lab and applied in solar cells. And also, we do some plasma modification in polyaniline with the graphite composite. And also, we develop some active layers like porphyrin in titania, and also develop modified also the titania itself for the host materials. And also try to revisit the absorption behavior for some dyes in the SSC, and applied also for silica material as internal refractor, for example, because one of the collection of our materials. Of course, adding the internal refractor, you add also the problems from the point of view of interfaces. And I think the last one, I think this is the research collaboration with Professor Natalita, passivation material using the crystalline nanocellulose as a biopolymer for perovskite passivation materials. Okay, maybe the conclusions, I can say that the PN junction and the space charge region model are the fundamental ideas for charge separation in PV devices. And the concept of PN junction is expanded and generalized to form a PIN junction, HCl active layer, ETL, and also the counter electrode electrolyte dye and ETL. The junction is no longer limited to metallurgical junction. It can be any interface that form in forming an junction, providing a space charge region that separate electron and hole and carries them to the electron circuit. Compatibility between layers is essential not only for creating an interface with a functional electric junction, but also for guiding a selection of materials and fabrication technique for this layer. So, as concluding remark, that means that if we develop many type of material, we have a large collection of ATL, ETL, active material, and also the method deposition for itself. I think, and then we collaborate with all our collaborators. I think we can solve the interface problem in this case. Thank you very much for the time. I will return back to the chair. Thank you.
Okay, thank you very much, Professor Fei, for the very comprehensive and very nice talk. I think I agree with what you said about collaboration. I think collaboration is quite the key to advancing the research in PV in solar cell in particular, because solar cell is quite a complicated device, so we cannot do this by ourselves. So we all need to work together. So now I would like to invite the audience to ask any question to Prof. Fei. So we have one question here from the audience, from Mr. Yuda Prima Hardianto. Are you there, Mr. Yuda Prima Hardianto? You can open your mic. Oh, can unmute perhaps the Someone, can you help to open? Yeah.
Okay, yes. Now
Yeah.
I'm able to unmute already.
Yes, please.
Okay, thank you so much for Miss Natalia for the chance, and also thank you so much for Professor Fenardi for very nice presentations. So it's very insightful talk, and basically, for me, I already asked for many times when there is a talk from BRIN regarding the photovoltaic or DSST, something like this. But actually, I'd like to get maybe another clear explanations. When you show the presentation of the Venn diagram for each material, so we can see that how each material, the Venn diagram can expand it or can be squeeze, something like this. But actually, I am really wondering how to measure this Venn diagram, because basically I'm not from the background of either DSST or photovoltaic. I'm from the battery, background. So that's why actually I'm wondering about how to measure, the Venn diagram of this specific material. So do we need to use a CV and combine with UVP, something like this, or is there another method to, obtain this Venn diagram? And also I'm wondering whether this one is, or it might be only from theoretical, expectations. So that's why actually that is still in my mind until now. Thank you so much, Professor.
Thank you, Mr. Yuda. Very good question. And Prof. Fei is an expert in spectroscopy, so I think he can answer your question very nicely. Please, Prof. Fei.
Thank you, Professor Natalita. Actually, because we say that when you ask about its optical band gap, I think the most efficient way is to use optical methods to determine the band gap itself. Of course, if you have like other direct methods, like for example, scanning tunneling spectroscopy or something, you can really have the band gap also. And then, for example, if you have XPS or UPS, X-ray photo emission spectroscopy, UPS, UVP photoelectron spectroscopy, but you need some inverse one. So you have like reflected electron energy loss spectroscopy to combine with this method. So I think if your sample is opaque, for example, if the sample is not transparent, or your sample is translucent, maybe you will not have multi-reflection. So you can use either the diffuse transmission diffuse transmission spectroscopy for UV-Vis, for example, or you can use the diffuse reflectance spectroscopy UV-Vis to determine the band gap directly using the top plot. So actually, it's very simple. But the problem is when your sample, where your film is transparent. In nice film, we talk with the silicon solar cell, for example, we talk about the perovskite solar cell, we talk about polymer solar cells. It is transparent. So that means you have a multi-reflection. So determine the band gap actually is not easy. So mostly people use ellipsometry to determine the band gap. But of course, after you have the spectra, you have to fit the spectra. And then you fit the model, and then after that, you get the band gap. So actually, it's not really direct. But, so people sometimes they compare with other direct methods. Of course, in some like photothermal deflection, still you have the interference fringes. Ellipsometry, you still have, for example, the transmission or reflectometry still have interference fringes. So the problem is when you have a transparent film or the very, very, how to say it, two coherent parallel plate that for with different refractive index, and then you use spectroscopy to measure their transmission or absorbance. Normally, you will have multi-reflection. That multi-reflection actually hinder you determine the band gap directly, so you have to fit with certain model. But the model actually is well developed. But sometimes we also use the interference fringes to determine the thickness. So that means if you use ellipsometry, actually is a quite complete system. As long as we really know about the materials, we can determine the band gap easily. But if you really have a new material that you are not sure about the dielectric function of this material. So sometimes people try to make a model and compare with the direct method. I think nowadays one of the most direct, I think the STS, scanning tunneling electron microscope, because you will have the CB and the VB directly, and then you directly measure the distance between the VB and CB, and then you can get the band gap. But the problem is that you probe with electric current, so it's like we cannot say it's really like optical band gap, but it's more or less like electrical band gap. In principle, actually, these two they are two are the same, but sometimes it's shifted slightly. So, but it's okay. So I think if you sample opaque, maybe I can conclude, if sample opaque, you can use DRS, or if it's translucent, you can use DTS. You can directly extract the band gap using the top plot. But if your sample is transparent, you have to use ellipsometry, but you have to fit. But if you have other, even using X-ray and etc., it's still problems. So I think these three optical methods, I think, is the best, and it's quite cheap comparing to other X-ray methods. Thank you.
Okay.
Maybe
Thank you.
if it's not clear, maybe we can discuss later.
Yes, thank you, Prof. Fortunately, we have very limited time, and maybe we have 1 or 2 minutes left. So yes, I would like to invite one more question. We have one question from Prof. Yusuf. Prof. Yusuf, ready? Can you open the mic? Yeah.
Okay, thank you very much. Okay, thank you, Prof. For your interesting talk.
Thank you.
Yeah, thank you very much. Maybe I have a short question relating this solar cell technology. So in this slide, you mentioned for the solar cell, we consider for the 3 parts: efficiency, stability, and upscaling. So the efficiency, yes, we know efficiency is more higher is better. Stability is okay. But how about the upscaling? What should we consider for to upscaling our solar cell devices? And as you know, we have the small solar cell, and we make a upscale. We hope to upscaling the solar cell. So what should we consider to the upscaling solar cell? This is the first question. And the second question is, the solar cell technology, it is possible, maybe in your perspective, is it possible to make the photo detector? What your comment relating this, relating the solar cell technology to make the photo detector for the red, blue, and green, or something like that, UV or something like this? Thank you very much. That's all my question. Thank you very much.
Thank you.
Thank you very much for the inspiring question. So sorry, Professor Natalita. Thank you.
No,
Okay, maybe
that's all right.
it's
I
okay
just
for
want
me
to
to
ask you to keep
directly
a
answer.
short answer.
Okay.
Yeah.
Actually, maybe I will answer first, Prof. Yusuf, about the second questions. Of course, if we can make a solar cell, you can make photo detectors. Actually, it's not so difficult, because for detector you don't need really high efficiency, but at least it has to be calibrated. That's all. That means that you have to be sure that because normally we will measure for the solar cell without load. Normally we will measure only the voltage, but we have to be sure that we measure the current. You can use the trans impedance amplifier, etc. So it's not so difficult. But to be sure that, but the problem is to be sure that for each cell has to be calibrated. That means because it's become detector, it's become the probes. So you can use any material. You can use material that work for solar cell, so it's okay. But for the first questions, actually it's challenging. Just like in my presentation, I said that for the solution base, normally the upscaling is okay. But because for the vapor base, we design a vacuum chamber, normally designed since the beginning for the maximum size of the wafer of the cells. For example, if you design the chamber for 10 by 10, so you cannot use for 20 by 20. But if you start design for 20 by 20, of course you can use to deposit 10 by 10. So the smaller one is okay using the larger chamber. But the problem, normally people try to design the most efficient chamber because the vacuum system or the vacuum technology is how to say energy consuming system. That means if those chambers become larger and larger, you need a higher pumping power, and it costs a lot of electricity. Especially in PV, we have to consider how much electricity that we spend to create the PV cells. In the end, we use this PV cell to generate electricity. So if it is not thermodynamically balanced, so it's not good. So what I can say that now the trend normally they will stick, for example, for the silicon solar cell, they will stick either 10 by 10 cells or 15 by 15 or maybe 10 by 5. It depends on the factory. And then after that, they make these cells and they array these cells become like there is some parallel and series in series. They will make array in parallel in series to become larger modules. So actually the cell is still 10 by 10 or still 20 by 20 or still 5 by 5. It depends on our system. So they don't enlarge the deposition system itself, but they try to have a good workflow. So we will deposit many cells per time. And then they try to combine these small cells, become larger module. Nowadays, the strategy is like that. So it's depend on the factory. Some factory 10 by 10, some factory 10 by 5, some factory 20 by 20. But the larger module, actually, they have many problems because some homogeneity, etc. So nowadays, many factories, they stick with 10 by 10. Maybe that's what I can answer. Maybe it's not how to say it, it's not complete, but so far that I know it's like that. Thank you very much. Sorry, I cannot give you a full answer. Thank you.
Thank you very much, Prof. And unfortunately, due to the time limit, I will have to end this session here. But please note that there are some questions in the chat box. So if you don't mind, could you please answer the question directly by typing your answer in the chat box? Okay, thank you very much, Prof. Nadiswendo, again for your time and your contribution and for delivering such an inspirational talk, and to everyone for your active participation. Thank you, Prof.
Thank you very much.
Okay.
Okay.
Thank you. Okay, now.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Yes, now let us move to our second session. So in this session, we will have a guest speaker from China, Professor Mingqi Wang. So before we start to listen to his talk, I would like to briefly introduce him. Professor Mingqi Wang obtained his PhD degree in physical chemistry back in 2004 from Chinese Academy of Sciences. He is now a full professor at Wuhan National Laboratory for Optoelectronics in Huazhong University of Science and Technology in China, and he has several impressive research experience in few countries, such as in Germany as Alexander von Humboldt Fellow, and then he was also a postdoctoral fellow with the famous Professor Michael Gretzel in EPF Fellows in Switzerland in 2007, and he was also a scientific visitor at UCLA in the US in 2016. His research interests include the development of next generation solar cell, especially perovskite and tandem solar cell. And he also works on electrocatalysis for hydrogen production and many materials innovations for high efficiency, stable and scalable photovoltaic devices. Good morning, Professor Mingqi. How are you today?
Thank you. I'm good.
Thank you very much for joining us today. It's nice to see you again. And as similar to the previous session, so today we'll have a maximum of 30 minutes. I have to limit the presentation to 30 minutes because I think many audience here are very interested to have discussion. So please, Professor Mingqi Wang, you may share your screen.
Okay, thank you.
Thank you.
Okay, can you see it?
Yeah, we can see. Maybe
Yeah,
you
thank you.
can full screen the screen, the
Yeah.
display.
Okay. Thank you, Chairman. This is Ming-Kui Wang, from Wuhan National Laboratory for Optoelectronics. First, I would like to thank Professor Nadina Nilsson for the brain for your very kind invitation to give me such a good opportunity to share our work with you. And this meeting is about the photovoltaic technology. So the topic of my talk will be focusing on the efficient and stable Photovoltaic solar cell. Just allow me just use a few minutes to introduce where I'm from. So I guess most of you are from Indonesia, right? So we are looking in the just put the middle here. At the middle of China here at calling Hubei province, and the Huazhong University of Science and Technology is in the city of the Wuhan. And the Hubei province actually is a very beautiful place to go, particularly in this autumn. So here just show you for some must go places in Hubei, since the Yangtze River pass through this whole province. So we are mostly talking about the water. So you can see that we have the yellow Korean Tower and also the three gorgeous dams, so which very beautiful place to go. And for the Huazhong University of Science and Technology, just celebrated his own 17th birthday. And even though it's a relatively young university in China, but the hostel has become one of the major or strong university with high rank in the range of about 300. The QS World University ranking in 2025. And the unit where I'm working, it's the Wuhan National Laboratory for Optoelectronics. And this actually is a research center on the high-tech technologies, for example, the laser and some optical imaging spectroscopy for the biomaterials. For sure, that for the energy is one of the most important part. And as Professor Nadina said, have been working in different places. I'm glad to see the last speaker talking about the dye synthesis solar cell. Actually, for me, I worked in this field since 2007 to 2013. So that's meaning I spent around 7 years working on this topic. 4 years with Professor Michael Grazer, and then we come back to China. I work in the host and try to set up my own group and trying to improve the efficiency and stability of this type of solar cell. After 2013, then I had to shift my research topic to the Photovoltaic solar cell. During that time, I had a visit to the Professor Yang group at the UCLA in the America. So let's getting started with the presentation, the efficient and stable Photovoltaic solar cell. I'm trying to speak as simple as I can because I must apologize if I have caused some kind of misunderstanding because of my accident. So as you might realize that China actually has become the leader in terms of photovoltaics. So the carbon peak and carbon neutrality has become one of the Chinese government, the national strategies trying to reach the target in the middle of this century. But this an issue to utilize the renewable energy source, for example, for the solar energy, because of this problem of this, for example, the uncontrollable and intermittent issues of this solar cell. So that means you cannot generate and use this electricity at the same time. Fortunately, this scientist proposes some sort of useful method to trying to use this electricity from the PV system. For example, use the water splitting driven by the PV system to produce hydrogen, which is one of the promising method or way trying to get the solve this problem of this intrinsic nature of this photovoltaic systems. So Photovoltaic solar cell actually is one of the largest, or the important topic we are talking about today. So what's the perovskite? Actually, this material has been discovered hundreds of years ago, then by a Russian scientist. So this most of the compounds used for the solar cell application actually has the chemical formula of the ABX3. So that means for the A site, it's the kind of the organic or inorganic component. It has the, for example, the cesium as the inorganic part, and for the set B is like the lead, the tin, or the other metal ions, and the X is that halide ions such as the chloride ions and iodides and bromide ions. So that's actually is quite simple component, but one of the amazing property of this material actually it can be, this crystallization can be tunable by changing that different component into the composition. So for example, it's due to the different size of the cancer into this component, you can easily tune that crystallization from the into this very stable phase. For example, the cubic phase of the perovskite. Normally, this kind of the material has a black color and also is stable. So that means it can absorb a lot of light. This actually is quite interesting, right? And the second one is that there's some of the people working on this kind of material is most focused on the different component. For example, the organic stuff for the A site. Here I just show you most of used component in the community, and also the influence from this organic component into this different physical property of this perovskite material, and showing this table. Maybe it's too small to read it, but still just keep in mind that actually it's quite plenty of this property of this material has to be discovered. And then another one point that particularly as said in the last speaker talking about the banding gap. So that's actually most of the time we pay more attention to tuning the banding gap of this perovskite material, trying to improve that net absorption ability of these devices. For example, according to the SQ limit, this kind of the most of the semiconductor used for the solar cell application, usually the band gap will be in the range of the 1.1 to the 1.6 electron volts. For your information, that for example, the silicon actually has the same band gap of 1.12 electron volts, and for the most of the efficient perovskite solar cell, the band gap for this material is about 1.2 to 1.6 electron volts. For example, here showing here the FA system actually is quite small, and it's about 1.5 electron volts for the banding gap. So that meaning we can tune that the banding gap that's also can answer that question from the audio saying that can we make a colorful devices by using the different components? Yes, for sure, we can make the different colorful material devices by selecting different materials from this as shown here this picture. So an important feature for the perovskite also is highly light absorption ability, as mentioned before, compared to the silicon. Actually, for the perovskite actually has very strong light absorption ability. So that means you can make a very thin film devices used based on this kind of material, right? And another one is that when we found that this material actually has a longer diffusion recombination lifetime, and also the longer diffusion length. So that's actually compared to the dye-single solar cell. This actually is very, very impressive, because in this case, that's why this device has higher open circuit voltage compared to the other thin film solar cells. So that's actually to be ensured that effectively charge collection. So therefore, most of the reported data showing that the perovskite material has another benefit, showing the defect tolerance. That meaning even though that there's so many surface state onto this material, still, for example, the device has shown high efficiency. So look at this. This could be related to the electronic states of this material. For example, by perform the DFT calculation based on the first sample, has shown that the 6 s orbital, that's the s orbital of the laser, actually contributes more onto the valence band of this material, and for the p orbital from the laser and the from the iodine contributed to the conduction band. So that meaning you can easily tune that the band gap, the size of the band gap of this material. Since this material has the defect tolerance, so most of the time when we're talking about the devices, we have to think about that the different the contribution from the inference or the inference of the recombination onto the device performance. For example, showing here we have a different influence from the factors onto the open circuit voltage and also the fair factor of the device in theoretically. So that means we have to think about that to reduce that. For example, the SRH recombination, meaning that this kind of the trapeze-induced recombination into the film, and also the surface recombination by using some sort of the surface modification, and most importantly, when we can concern that this perovskite solar cell actually is one of the type of the thin film solar cell. So that means that we have because it's most of the time the film is made by the solution processable method, for example, spin coating. So that means there's some of the grains into the thin film. We have to think about that the grain banding and also some sort of the defects along this banding. So that's one of the biggest issue we have to think about it. So that's why I just show you one of the same image showing that how the perovskite layer looks to be. Sorry, I didn't put the scan bar here. Normally, this particle grains shows in the range of the few hundreds micrometers. So that meaning it's one of the target to trying to modify or surface modify onto this grain size. So this year actually, I show you again this power conversion efficiency for different type of solar cell, but we are focused on this perovskite cells. This year actually, the highest power conversion efficiency of perovskite cells is close to 27. But some people saying, okay, maybe over 27%. So that meaning actually it's quite high, right? It's very high value for the thin film solar cell, because compared to the other type of solar cell, the perovskite cells actually already reached absolutely high values. And the attraction of the perovskite cells is not only its high efficiency, but also it can be made by solution method. For example, it's a solution processability. So that meaning you can easily make fabricated devices use the technology in the common laboratory. For example, spin coating or deep coating. Even with Dr. blading, you can make highly efficient devices. And also, as mentioned previously, this also can be made by the vacuum deposition technologies. That's actually, it's also another like a physical deposition method. So actually, most of them measured, for example, from the solution, for example, speed coating actually are valuable in the common laboratory. That's why there's so many research group just jumping into this community, this field, trying to improve the efficiency of these devices. And the second one, I think, because it can be made in a cheap way due to the low requirement of the whole fabrication process. As mentioned before, as we know, the launch from the silicon-based solar cell, because for fabricate silicon cell, you need a long industrial name, I mean, to finish the last job. But for the photovoltaic solar cell, it may different, and it may be made fabricate in a low cost way. So that's why there's so many so interesting topic recently in the scientific community. So some people saying that this cell will be commercialized soon, maybe this year or next few years. This actually it's here I just show you some example. For example, the devices at different size can be made produced with the help of the technology called solid die coating technology. For example, use this coating technology, you can deposit the photovoltaic layer at a different size. I show you here from the micro this 1 centimeter. I mean, this the length 1 square centimeters to up to the 10 by 10 square centimeters. I mean, this is like a submodule cells up to in meters. I mean, the size, the length or the width. That's a big one. That's meaning just by using this kind of technology, you can deposit different layers. So that's meaning the commercialization of this photovoltaic cells will not be, I mean, a bigger issue. I mean, according to the ability we have now. But however, I mean, before a successful massive production of the photovoltaic cells, we need to face following some huge challenges. The first one is that the stability. So now if some people think, I mean, according even Zoom, I mean, our group, my group, also the students say that the photovoltaic cell is stable, but still the most stable reported photovoltaic cells so far is much unstable compared to the silicon cell. I mean, maximum 2 years, 3 years, compared to the 25 years. I mean, for the silicon cells, I mean, there's a large room to reach the stable cells. And some researchers have already pointed out that the effect of the oxygen, light, even the moisture, I mean, water have effect of the stability, even that the intrinsic behavior of the perovskite also play and determines that the stability of this devices. So that's meaning there's many steps to go before achieving the stable, I mean, product. The second one is about that effect of the environmental. So we build the solar cell and try to serve the environment, but here photovoltaic solar cell, I mean, highly efficient photovoltaic solar cell using that compound which has the most of the time containing the lead, which is strictly forbidden in most of countries. So that means the scientists need to find candidates towards the lead-free to replace the lead-based perovskite. However, according to the reported data, the lead-free actually the perovskite cells show much low efficiency. I mean, with the highest value, it's about 14% actually from my group. in which the inorganic perovskite, the tin, season tin iodine with a suitable band gap about 1.4 electrovolts is used. So still, we need to work more about this component, trying to get the friendly material. And the third one, again, similar to the dye synthesis solar cell, in my opinion, actually the interface, it's quite an important issue. In a perovskite solar cell, as according to the structure here, there's many interface to construct the pathways for charge transfer, and also, of course, for the recombination as well. Just remember the one important thing that this device is quite thin. So that's only 1 micrometer and less than 1 micrometer thickness. So therefore, how to precisely control the interface between the perovskite layer with the function layers is quite important. And this interface actually determines that the efficiency of the charge collection and the charge recombination. Just show you one example is that the compact layer between the T-cell glass with the perovskite layer. This thickness is about 30 nanometers. It's composite by the nanoparticles, which is around less than 10 nanometers in diameter. So that means we have only 8 nanometers together to construct a thickness of 30 nanometers, right? So that means the if you look at the as the image showing here, that the particles are not being it's not very compact. They don't contact each other very well. So that means you have to think about find a suitable way to enhance that the electron transfer from the one single nanoparticle to another one. That's actually quite difficult to achieve this kind of sense. And also that for the charge transfer for the different interface actually is quite faster compared to the other system. For example, for the dye synthesis cell, that recombination of time is longer. For the back recombination is longer compared to the what's happening in the perovskite solar cell. So that's actually you need to think about more about the interface. So that's the 3 very important issue actually for me to try to find some solution to do them. So here I just I'm going to show you 3 examples that we carried out in the neighbor, trying to achieve efficient and stable perovskite solar cell. And the first one is about the modulating the current interface to achieve the efficient solar cell. So just as mentioned before, the perovskite layer actually made by the solution process, for example, speed coating technology method. So that's this layer actually represents a compact layer that's usually is made by the metal oxide, for example, tin oxide, onto the T-cell glass. So that's since the compact layer, or some people calling the charge selective layer, actually has totally different property with perovskite material. So that's actually the interface will be very important here. Normally, the people working on the top layer of the perovskite, because it's easy to modify or tune the property of this top layer. And for the bottom layer, actually, it's not easy because you just directly inject the solution of the precursor solution onto the titanium dioxide layer. So that means it's not easy to tune that the buried interface. So we think that this is quite important things to do, because at the interface there's some of the under-coordinated states. For example, the PP, the later 2 classes, means that it's not saturated by the neighbor atoms, so it's like a defect. And another one is that the iodine ions means that always transfer from the place where it is, then to form the intersection iodine. That's the another type of defect. And the very here, the bottom layer of the perovskite. I mean, when those two defects contact with the tin oxide, the charge transfer layer, it will determine, I mean, decrease that the stability or the efficiency of the charge collection at this interface. So actually, this is the starting point of this experiment. So what we are doing that is like this way. We propose that using the molecular, which has the push-pull structure, actually is quite common structure for the solar cell application. We selected the three molecules based on the aminium benzene derivatives. That means we modify this element here, tuning that the amount of the phone range from 1 to 3 and to 7, number 7 of phone range in the parent site compared to the amine site here. So this actually phone range actually has a benefit of the given the electrons. And here this actually has another learning electrons for the nitrogen atoms here. So that case we have this we can build up this electron push and pull structure. So this actually can be reflected by the calculation, use the DFT calculation showing that the electrostatic potential mapping showing here. So most of the time that's in the range nearby the phone range here, it has selective potential. That means it's easily to delete that the electrons, right? And in the other side, you have this nitrogen here, so it has a higher, relatively higher potential. That means it's easier to give this electron. So compared to these three molecules shown here, the C3F7 actually has a stronger ability to absorption the electrons or given the electrons. So actually, this is also agree with that the calculation on the dipole moment showing that the C3F7 has the highest dipole moment in these three samples. It's reached to the 12 Daltons. So that means this the ability of the molecule has totally different. This when put this molecular onto the tin dioxide and between this perovskite layer, we use that the XPS as the tool to understand that the interaction between the native element with that the molecular. As shown here, this actually by adding this photovoltaic component into the between this interface, we see that actually for the 4F operator for the native species shift the binding energy to the known levels. That means we have this ability of this interaction between this perovskite with this molecular, and also we similar behavior for the iodine, but the binding energy shift to the higher values. So we use that the this molecular, I mean, trying to figure out that the influence on the photovoltaic performance. So we use the different solution with tuning that the molar concentration of the three molecular and make the devices and compare the efficiency. So that's for the C3F7, this molecule has shown the best performance and it's the concentration of the 0.02 molar per liter. So then for the next study, we selected this molecular at this concentration for the further study. And also this result showing that the molecular of the C3F7 has the best effect on the preservation of the barren interface. So when we make the devices and use that different perovskite with tuning that band gap. So from the 1.54 electron volts to 1.6 electron volts and to the 1.68 electron volts for the perovskite component. and made the devices and measure it, and this efficiency actually is about the 25% efficiency. Most important thing is that the voltage actually has been increased largely compared to the control one here, showing that the 50 millivolts enhancement here. And the important thing that's showing that the according to XQ limit, we have the reached 95% of the XQ limit. So that's actually is quite impressive because it's the highest value reported so far. And this showing here the stability of the devices. It's quite long time, 1,000 hours under continuous illumination at maximum point text here at the temperature of 15 degrees. The reason why this in voltage has been increased, we use the cavern microscopy, trying to figure out that the charge accumulation at the interface and also the influence on the Fermi level for the this kind of modification, and also the recombination by the photoilluminescence measurement, and also the TRPL showing that the recombination of times has been increased. So it's totally showing that actually this kind of the photoluminescence quantum efficiency yet, and also the quantum Fermi level splitting into this at the bearing interface. So that means it's actually the contribution from the bearing side is about 26 million electronvolts. So since we have this smaller devices, then we fabricated another one, bigger one, size in 1 square centimeter. So the efficiency is about 22, with the impressively that the voltage actually does not change too much. I mean, normally for the larger one, the VOC will be decreased, but here we don't see too much decrease in the voltage. So that means we can use the device to drive sort of the water electrochemical electrolyzer. For example, we selected here is for the CO2 reduction towards the CO, the carbon monoxide. So that's actually is quite difficult job to do, because it's actually for the CO2 reduction, it's not easy to achieve the highly selectivity. So we use the two photovoltaic solar cell in series connected with this CO2 reduction electrochemical cell system. It's achieved at around 11.7% of the CO2 mesona to the cell conversion efficiency at the 2.1 volts here, and this system looks to be stable till to 15 hours. I mean, prove that the robustness of this from the PV driven electrochemical system compared to other reported data showing that the using the tender solar cell, we have the achieved about over 11% efficiency, and compared to this other three connection. So that's meaning showing that the advantage of this cell, if we can produce the devices which has higher open sector voltage for the for example, for the water splitting system application, right? So that's actually one of the example. Second one, maybe I can make it faster about the token. So we use that visible night waiting.
Excuse me, Professor
Yeah.
Mingqi.
We have
I'm sorry
1 minute. Yeah,
okay.
just quickly.
Only 1 minute. Yeah.
Yeah. So we just use synthesize different polymer, which is can be is easily to start a reaction. I mean, combine this repair that's corrects produced in the flexible solar cell by using that the visible light. And here just showing that quickly showing that the data we have. And the third one is we use that the another polymer which has this lots of plenty of the component of a polymer, trying to passivate the perovskite, also increase that hydrophobic property of this surface. As showing you that since here we have this radio that the perovskite can be safely, covered by this kind of polymer for at least 1 minute, right? We just put this 2 pieces of the sample, which is covered by the perovskite on the ideal glass. So for the control 1 minute, that conventionally made the pieces of the perovskite layer, it turns into the yellow color. That's for the PBI2. But for the material containing that polymer, so it can maintain that color till to change the color to, after 40 or 60 milliseconds, right? So that's demonstrates the stability of this material. So that's the efficiency is about 26 efficiency, and also it's very stable on different conditions. So let's can make a short conclusion. So I just give you the 3 examples, but only one. So detail, we can increase that open circuit voltage for the perovskite solar cell by using that functional groups, function molecules or polymers, and to increase that stability and also the efficiency. So and also this actually some examples we have in my group. Also, we are working on the trying to make a bigger cells. For example, using the laser sintering technology, we can try to fabricate the 1 meter times 2 meters. The large scale devices, and also trying to introduce that the PV water splitting system with companies. Try to commercialize this kind of the technology. Okay, sorry, just slowly, but I would like to thank the funding support and also my collaborators, particularly for the Professor Lazarudin from the EPFLO, and also Amant from the SPAM. And also thank you for your listening. I would like to answer any kind of question from you. Thank you.
Thank you very much, Professor Minghui, for the very nice talk and very inspiring, I think. And to briefly summarize your talk, I think Professor Minghui emphasized the importance of interface engineering to improve the charge transport and to minimize recombination in the device. And he has introduced some of his work, which is very impressive, and also I think would be very inspiring for us all. Okay, thank you very much. And now I would like to invite everyone from the audience who would like to ask a question to Professor Minghui. You can ask directly by raising your hand or writing in the chat box. Okay, I have one question from the audience from Pak Wilman. Okay, please, Pak Wilman.
Okay, okay, thank you. Prof. Minghui, nice to see you again.
Yes.
Yeah, I have 2 questions, Prof. First about the CO2 reduction. So it's very nice result that you have. So I'm wondering what kind of electrolyte that you use there in your result. Is it done on basic condition, and how you the solution, the electrolyte, how you prepare it? Is it you need to bubble with some CO2 first, or how is the preparation? And the second is I saw your PV water splitting system in your last slide. Can you explain more about? So I saw a tube, I saw a PV, I saw a tubular tube. So how is the system actually over there? So thank you, Rob.
Okay, excellent question. Yeah, very detailed. Yeah, for the CO2 reduction here, I remember that the catalyst for the electrochemical system, we use that the tin copper alum, as the catalyst for the CO2 reduction, and for use the nickel arrow LODH, that's for the double layer hydrogen, right? That's kind of the typical catalyst for the oxygen evolution. So the solution electrolytes into the system is the CO2 bubble, right? That you're right. So CO2 bubble, the 0.1 molar the positonial hydrogen. So that's meaning no, that's for the if you remember, it's that the should be KHCO3, right? That's the 1 molar. So that's the for the electrolyte. And usually for the I mean for this type of the in the laboratory we are trying to increase that the efficiency as much as we can, so that we have to think about the science of the the output power of the perovskite cells. Compared to the electrolytes here, because it's not easily, because we didn't put any other electrical element between these two systems. So just connect them, so trying to reach the maximum point here. So that's one of the important things we have to think about this kind of the system here. About the second question, we trying to cooperate with a company which the Fengfan, we call it the name, in the Wuhan the city. So we use that the PV system. For example, we have silicon cell, we have the converter, electronic converter. Put the voltage and the current, and we have the system between this the electrolyzer here. That's the volume is about we can produce 1 cubic meter of the hydrogen in a given time. That's about 4 hours. That's the capability of this system. So that's meaning the connection between this PV system with the electrolyzer actually is not the same what we have done in the laboratory. I don't know if it's clear or not for you now. Hello?
Yes.
Yeah, thank you. Thank you, Prof. It's
Yeah.
clear enough.
Okay, thank you, Prof. Mingkui and Pak Wilman. Unfortunately, we have a very limited time, but maybe I can allow one more question. So, okay, maybe a question still on your first work about the push-pull organic molecule for the tin oxide passivation and the interface specification. So there's a question in the chat box from Payuliar about the design, molecule design. So could you please explain about the guideline for the push-pull molecular design that is suitable for this kind of modification, in a sense that it will passivate and reduce the interfacial energy barrier? And I also have a question similar to this. You mentioned that the use of these 3 molecules can improve the VOC, the voltage, but how about the long-term stability and also the hysteresis index? Is there any effect on that with the use of these molecules? And also about the price consideration, is there any, can you show us what's the price of these molecular precipitors? Thank you.
Hey, that's yeah, that's for sure. Thank you. That's a very good question, because for the the design and also the principle why we have this sort of the molecular. Actually, this for us, we think that since this kind of contact between this let me put the full scheme here. So we have this tin dioxide, for example. This is electron transport layer, and this is we have the perovskite layer, which is the lead isober here, right? So in principle, the electron transport from the conduction band of the perovskite layer should efficiently to the tin dioxide. But as mentioned, tin dioxide has a different conduction band energy level compared to the perovskite. No, mostly there's 400 milli electron volts difference between them. And also another point is that the material property is different because the latency, for example, the latency constant of the tin dioxide is totally different with that the perovskite material. So that meaning we have to think about two things. One thing is that the energy level, the element between them. The second one is that the how to reduce that the mismatch of the latency of between them. So to design this kind of the molecular, what I'm thinking is that introduce that the push-pull structure. As far as we know that the push-pull structure, meaning as shown here, the electron transport between, for example, from this side to this side will be much easier if we just consider another molecular, because the push-pull structure will have its own electricity field into the molecular as dedicated by the dipole moment of this molecular. So that means the molecular has higher dipole moment, meaning that in principle it will change that the surface property of this substrate here. So that's one of the principle of this to design this molecular. The second one is that I'm trying to figure out that the length from the for example the top point here, that's for the aluminum group here, to the bottom one here, that's for the foreign function group here. So we selected this benzene ring in the middle. That means the benzene ring actually has a big pi conjugation structure, right? So that means that the electron transfer port along this carbon chain will be efficient as much as it can. So that's why this three molecular working very well into when we bury this molecular between this perovskite layer and the tin dioxide. This is actually one of the design principle of this molecular. Also, that you have to think about this interaction between this function group with that the perovskite layer, or and another term with that the tin dioxide layer. That's actually similar design structure now. Most people use that safe assembling layer for fabricate the even higher efficiency devices. And for the stability, I think this material actually is quite good. And as far as we know that by using this molecular into our experiment, showing that the stability of these devices under the continuous illumination measured at the maximum point. So that's it maintains that over 90% of this initial values. That's actually quite important. Stable devices, what we have already observed, and compared to that, without the modification, you see that actually for the control sample as shown here by the SEM image shown here, actually this kind of the correct at the bottom of this layer between that the electron support layer with the perovskite layer. That could be one of the reasons why the control sample is not as stable as with that the device which has the C3F7 molecular. So that's actually the effect of this molecular. So that's I think what there's more. I mean, some part I didn't answer more. Well, I just finished what. Yes.
Yeah, just a short question about the price range of, because usually the organic molecules are known for its high cost. So between these three molecules, yeah.
Yes, right. That's actually quite important. That's I mean, still, for example, that's not only organic stuff, but still here in the laboratory we fabricate the devices, use the for example, for the contact electrode, it's kind of silver or even gold. So that's also is quite important, expensive. And for example, use another organic stuff. For example, talking about this spirometat, which is used for the solid state device fabrication. And now the price actually has been dropped a lot. You can, in China, you can buy this kind of chemical at the, for example, 200, 300 yuan. So that's meaning $50 per grams in China. You can have it. But in the future, for the large scale commercialization of this technology, I don't think we can afford this kind of price. That's for sure. So that's why we have to work more, trying to get find another other replacement for this kind of issue.
Yes, yes. Thank you very much, Professor Min Kui Wang, for your very insightful talk.
Yeah,
Thank you again. And actually, we have one more question in the chat box. If you don't mind, could you please answer directly by typing it in the chat, because we have very limited time. Thank you again for your contribution and your time in this session. For everyone, let us give a round of applause, a virtual applause for Professor Min Kui. Thank you, Professor Min Kui.
Professor Nadira.
Wish you all the best for the future. Okay, so with that, I would like to conclude our session, the second session. And for the next agenda, we will have a short break, very short break, I think maybe around 5 minutes. And we will see you again on the third session, the Young Scientist presentation session. Thank you again, everyone, for your active participation. Thank you, and I will see you again. Assalamualaikum warahmatullahi wabarakatuh.
Kawasan Sains dan Teknologi Samaun Samadikun Bandung, sebuah pusat inovasi dan riset unggulan di Indonesia. Di sini masa depan ilmu pengetahuan dan teknologi dirancang dan dikembangkan melalui fasilitas mutakhir dan aktivitas riset yang beragam. Di kawasan ini terletak laboratorium riset terpadu kami, tempat di mana periset dari berbagai disiplin ilmu bekerja sama untuk memecahkan tantangan kompleks. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun dilengkapi peralatan canggih yang mendukung riset dalam bidang informasi, komunikasi dan teknologi cerdas, memperkuat sektor transportasi dan teknologi lainnya. Riset kecerdasan buatan, mekatronika dan elektronika di sini mendasari pengembangan teknologi masa depan, memungkinkan Indonesia bersaing dengan sistem artificial intelligence global. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun juga menjadi pusat riset kegempaan, pemetaan sesar, tsunami, gerakan tanah, serta kajian risiko dan resiliensi bencana untuk mengurangi dampak bencana geologis. Selain itu, riset iklim dan atmosfer yang dilakukan mendukung mitigasi bencana alam, pengelolaan lingkungan, dan pencapaian tujuan pembangunan berkelanjutan. Fasilitas pengujian untuk memastikan bahwa teknologi dan produk baru memenuhi standar kualitas dan keandalan yang tinggi. Di kawasan ini, tempat di mana ide-ide baru lahir. Kolaborasi antara periset, industri, dan mitra internasional menciptakan solusi inovatif yang berdampak luas. Selain itu, kawasan ini dilengkapi dengan coworking space yang dirancang untuk menciptakan lingkungan kerja yang produktif dan kolaboratif bagi sivitas BRIN dan para kolaborator. Fasilitas di kawasan ini telah memenuhi standar pelayanan publik, mencakup tempat ibadah, parkiran, dan toilet khusus disabilitas, tempat menyusui dan daycare, kafe, serta fasilitas kebugaran baik di luar maupun di dalam ruangan. Kami juga menyelenggarakan seminar, workshop, dan pelatihan untuk meningkatkan keterampilan para periset dan SDM pendukung riset, serta berbagi pengetahuan terbaru dengan masyarakat. Kawasan Sains dan Teknologi Samaun Samadikun Bandung adalah salah satu bentuk komitmen BRIN untuk memajukan ilmu pengetahuan dan teknologi di Indonesia. Dengan fasilitas modern dan aktivitas riset yang beragam, kami bertekad untuk menciptakan dampak positif melalui inovasi. Bergabunglah bersama kami dalam merancang masa depan yang lebih baik melalui riset dan teknologi. Kawasan Sains dan Teknologi Samaun Samadikun Bandung, di mana ilmu pengetahuan dan inovasi bertemu.
Research Center for Electronics is part of the Research Organization for Electronics and Informatics at BRIN. The Research Center for Electronics, or RCE, is home to 8 research groups that work together to explore new ideas, develop innovative tools, and contribute to national development through electronic science and technology. Advanced photovoltaic and
Good morning, ladies and gentlemen. My name is Adita, a researcher from Research Center for Electronic National Research and Innovation Agency, Indonesia. I am the chair of this session. In this session, we will have 3 young scientist speakers and 1 distinguished speaker from the Osaka Institute of Technology, Japan. Now we are going to young scientist speaker. The young scientist speaker will deliver a presentation for about 10 minutes, continued by 5 minutes discussion. Our first speaker is Mr. Siadi Tri Utomo from the Graduate School of Multidisciplinary Science and Technology, Institut Teknologi Bandung. He will talk about anti-solvent strategy for carbon-based lead halide perovskite solar cell. Let us warmly welcome Mr. Siadi. Screen is yours.
Okay, can you hear my voice, Miss?
Oh, yes.
Okay, thank you, Miss Adita. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone.
Waalaikumsalam warahmatullahi wabarakatuh.
My name is Siadi Tomo from Bandung Institute of Technology, and today it's great privilege for me to present at the second symposium on advanced photovoltaic 2025. And I will discuss our recent work on anti-solvent engineering in perovskite solar cell, where we introduce a polymer donor-driven anti-solvent strategy to enhance both device efficiency and stability, particularly with for architecture with printable carbon electrodes. Next. Okay, here's the outline of my talk. I will start with an introduction about perovskite and the role of anti-solvent. Then I will show how adding polymer donor influence MAPBH3 film characteristic. Next, I will present the device performance and optoelectronic result. And finally, I will close with the key finding and conclusion. Next. Perovskite are fascinating material for solar cell, especially the ABX3 perovskite structure consists of tunable acid cation as methyl ammonium, formamidinium, and calcium, beside metals such as lead and tin, and excite halide as iodine, bromide, and chloride, where compositional choices directly influence band gap, stability, defect formation, and device performance. Perovskite are exciting because of their unique properties, a very high absorption coefficient, high diffusion length, and high mobility, tunable band gap, and tolerance to the defect. They have the general ABX3 structure, and among fabrication method, the one-step deposition process is attractive for scalability process. However, it requires very careful control to ensure high quality balance. Next. So in the one-step process, the anti-solvent is a more crucial step. It controls crystallization, improves morphology, and reduces pinholes and defects. But there are limitations. Reproducibility is not always reliable. Scaling up is difficult, and the defect control is still a challenge. So we ask, how can we make the dissolvent step more effective? So the strategy with us in the next slide. Okay, next. And to overcome these issues, we propose a polymer donor-driven anti-solvent strategy. And the idea is quite simple. These donor polymers can coordinate with lead ions during crystallization, slowing the process and allowing larger grains to form. They can also precipitate under coordinated lead and halide defects, resulting in small and uniform films. And because the polymers have hydrophobic side chains, they can provide extra protection against moisture. And altogether, this should improve charge transport, carrier lifetime, and device stability. So on the right, you can see the chemical structure of our junior polymers, such as PM7, PM6, PCE10, and P3HC. And these polymers are already proven in organic solar cell. However, and that is exactly the gap we are trying to address in this work. Next. So before showing the result, let me briefly explain our experimental approach in the one-step deposition method for methyl ammonium lead iodide perovskite. We normally use an antisolvent like fluorobenzene to control the crystallization process. What we did differently was to dissolve very small amount of polymer donor into the antisolvent, and we test for polymers such as PM7, PM6, PCE10, and P3HT, each at the concentration of 0.5 milligrams per milliliter in chlorobenzene. Next. And now let's look at how the polymer additives influence the film structure and surface chemistry. And from the XRD measurement, all the samples show the characteristics of tetragonal MAPBE3. So the crystal phase is preserved even with the polymers additive. This is important because it tells us the additives are not disrupting in the basic perovskite lattice. When we move the XTS, we see something more interesting. The PB4F and I3D peak shift towards lower binding energies in the polymer treated films. The shifts indicating a stronger interaction between the polymer and the perovskite surface, which helps in specifying the defects. Among the four polymers, PM7 shows the stronger shape, followed by PM6. So, in the structurally, the perovskite remains intact, but at the chemically, the donor polymers clearly interact with the surface to reduce the defect. Next. And the XPS also confirms the presence of donor polymer at the surface. The C1S spectra shows stronger CC signal in the treated film compared to the pristine film. This means the polymer are not just present in the solution; they actually integrate at the film surface. And this surface modification is more crucial because many of the performance losses in perovskite solar cell originate from the surface defect. Next. And the FaceTime image make the improvement very clear. The pristine MAPBE3 films show small grains and visible crack. In the contrast, the polymer treated films are more compact and uniform. And as you can see, PM7 gives the largest grain and the most compact morphology, followed by PM6, PC10, and P3ST film. Larger grains and fewer cracks mean fewer crack sites and better pathways for charge to move, which should directly improve device performance. Next. And here we compare the optical properties of the films. On the left, the absorption spectra show that all samples have very similar absorption age, around 750 nanometers, which correspond to the band gap of about 1.6 electron volt. And this means the band structure is not significantly affected by this additive. So the bigger difference appears in the photoluminescence, as you can see, PN6 and especially PN7 treated device show much higher PL intensity compared to the pristine films. This is a stronger emission indicates that non-radiative accommodation is suppressed, meaning fewer traps and better device specification. Next. Let's look at how these polymer donor additives affect the device performance. Here we compare the photovoltaic parameter, GSC, fill factor, VOC, and overall power conversion efficiency. The results show that all polymer additives improve device performance compared to the pristine MABBE film. The improvements mainly come from higher GSC and better fill factor, which are linked to enhanced charge extraction and reduce recombination. Among the four polymers, PM7 clearly gives the best performance, with PM6 also performing strongly. On the other hand, P3HT improves performance less significantly, and in some cases, even introduces leakage currents, which reduce the overall gain. Next. Here we analyze the trap field limit voltage, or PTFL, which allow us to estimate the trap density in the film. So the most significant improvements comes with PM6 and PM7 treated device. PM6 lower PTFL to 0.45 volts, cutting trap density to 1.8 times to 10 to 16 traps per cubic centimeter. And PM7 performed even better, reducing PTFL to just 0.36 volt with a trap density of only 1.4 times 10 to the 16 traps per cubic centimeter. So the key point is PM7 and PM6.
Excuse me, Adi. Sorry, you have 1 minute left.
Okay. Effective additives during crystallization, minimizing defect formation and improving the electronic quality of the perovskite layer. So next. Okay, now let's look the photovoltaic performance in more detail. On the left, you can see the box plot over each PV parameter. And at the right is the stability test in nitrogen condition without encapsulation. The control device dropped quickly, and P3HT degraded even faster. In contrast, PM6 and PM7 device retain over 87% of their initial efficiency after 2,500 hours. This demonstrates that polymer donors not only improve performance but also significantly enhance long-term stability. Next. Okay, the first, as you can see at the EKA, TN6, TN7, and PC10 give strong response in 400 to 700 nanometer range. That means better photon to electron conversion compared to the control NT3HT. Second, the WGV curves, leakage current is strongly suppressed with PM6 and PM7, but P3HT actually increase the leakage. Third is result in the semicircle form. PM6 and PM7 are larger, which means higher recombination resistance and lower series resistance. And finally, the transient photovoltaic PM7 device show the longest carry lifetime, about 0.4 seconds, followed by PM6, P3HT, and contrast has the shortest lifetime, showing fast recombination. Next. And to summarize, polymer donor additives act as effective anti-solvent assistant, leading to improved crystallization, larger grains, and more compact film. Optoelectronic analysis confirmed that the donor polymer treated device successfully reduced the trap density, enhanced charge transport, and longer carry lifetimes. And finally, device with PM6 and BF7 deliver higher efficiency and stability compared to the control and PTSD treated device. Okay, that's all for my presentation. Thank you very much.
Okay, thank you very much, Adi, for your excellent presentations, and congratulations on your successful research using the polymers. Okay, let us continue to Q&A session. Okay, we have one question here from Mr. Widya.
Okay,
Mr.
thank
Widya,
you.
time is yours.
Okay, thank you, Miss Dr. Adita. So I have question that you use positive TP type polymer for anti-solvent additive, and then we usually use this material for whole transporting material. So in your opinion, it will be how is we also combine this material as a additive, and we use together as a whole transporting material. And then the second question, the effect that you expect it will be as passive perovskite, or it will be help the whole extraction. Thank you.
Okay, Adi, you can answer directly.
Okay. So thank you, Mr. Vidya, for the question. The polymer donor is can act as a whole transfer material for the perovskite, but in this work we work the anti-solvent strategy to combine with anti-solvent to passivate the perovskite layer. So the principle are differently, but the whole transfer material are specifically designed and as an interlayer film deposit on the top of the perovskite, and the main role is the extract hole for the N electron blocking layer from the perovskite. So the donor polymers act earlier during the film formation process, and the primary role is to the control crystallization to inlet grain and precipitate the surface defect. So the mainly improve film quality and defect density. Um, if we combine with conventional ATM, whole transfer material, the effects can be synergistic. The polymer improve film crystallinity and reduce scrap, which prolong carrier lifetime, especially at the whole transport for the perovskite layer. and they had the whole transport material then operates more efficiently because the interface has fewer recombination center because there are many act to blocking the electron to the carbon electrodes, and the result is reduced interfacial recombination and more efficient whole extraction and maybe better long-term stability. Sorry, and the second question?
Okay, that's all.
Okay, thank you.
Okay, thank you, Adi, because actually we have one more question in the chat box, but because we are running out of time, we have to continue to the next young scientist speaker. Thank you very much, Adi, for your contribution in our symposium. Please give applause to Adi.
Okay, thank you, Miss Adita.
Okay, let's move to the next presenter. Miss Rosaila, are you there? Rosaila.
Hello, can you hear me?
Yes, okay. Okay, Miss Rosaila from Physics Engineering Department, Institute Teknologi Bandung. She will talk about the effect of polyvinyl alcohol additive in tin-based perovskite solar cell. Please welcome Miss Rosaila. The screen is yours.
Okay, thank you, Miss Adita. Good afternoon, everyone. Let me introduce myself. My name is Roshela Masna Muslimawati, and I am a doctoral student at Institute Teknologi Bandung. So today I'm honored to present our research on tin-based perovskite solar cells, especially the effect of polyvinyl alcohol or PVA additive and device simulations. Under the supervision Professor Natalita Maulani Nusa, Dr. Muhammad Haris Mahyudin, Professor Yoshiyuki Yamashita, and Professor Ahmad Nuruddin. Please move to the next slide. Okay, thank you. Perovskite solar cells are rapidly evolving technology, as we can see from the significant increase in the power conversion efficiency, or PCE, over the last decade. This graph shows how perovskite and tandem perovskite silicon cells have surpassed traditional silicon cells in terms of peak research efficiency, reaching over 30%. Perovskite materials possess several key characteristics that make them ideal for solar cells. They have a high absorption coefficient, large charge diffusion length, high hole mobility, and high electron mobility, and also can be synthesized using simple and inexpensive methods. However, a major issue in is their high toxicity, primarily due to the use of lead or PB. This next to the okay, thank you. To address the toxicity issue, our research focused on lead-free perovskites, specifically those based on tin or SN. This table compares several lead-free alternatives to the lead-based perovskite. While tin-based perovskite currently have a lower efficiency than lead, they show great promise with the band gap close to the optimal range for solar energy conversion. So the key challenge, can you next? The key challenge with tin-based perovskite, go back please. Okay. The key challenge with tin-based perovskite is their stability, as shown in this degradation mechanism diagram. Tin iodide is prone to oxidation into the tin dioxide or tin O2 when exposed to the ambient air and moisture, which degrades the device performance. Okay, next. So the highlights the current research status of formamidinium tin iodide or tin-based perovskite material. The main keywords and the topics are first, degradation. Several articles focus on the degradation mechanism of hybrid tin-based perovskite solar cells, specifically the role of tin iodide. This is the big challenge in tin-based perovskite research. And then oxidation control, one key area of research in the inhibition of tin2+ oxidation in the perovskite solar cells. In the perovskite solution, this is the crucial step for improving device stability. And then how to improve efficiency, the research also explores various strategies to achieve highly stable and efficiency perovskite solar cells, such as design of the perovskite solar cells. Okay, move to the next slide. The energy band diagram shows that misalignment in the energy levels can lead to higher recombination of electron and holes, which reducing the device efficiency. The research identifies bulk and interfacial defect densities of absorber layer as the primary factors limiting the device efficiency, and then the impact of doping concentration, electron affinity, thickness, and interfacial defects on the perovskite solar cell performance. Okay, let's see to the table. Comparing two perovskite solar cell structures, which is aluminum FTO WS2 tin-based perovskite, zinc phosphate, and nickel, achieve PCE of around 29% in 2024 study. In contrast with the same material, Yin et al. Report that for this material is only 17%. So, based on these findings, the research has two primary objectives. The first one is to control stability of tin2+ ratio of tin-based perovskite solar cells using PVA additive, and then to design the structure of perovskite solar cells using a simulation method. Our experimental work involved two synthesize process. One of the pure perovskite or pure FASNI3, and then the other one is with PVA additive. Both process involve dissolving the precursor materials in DMSO or dimethyl sulfoxide and stirring them in two kind of stirring. There is overnight at room temperature and then 2 hours at 60 degrees Celsius. The final films were prepared using spin coating technique followed by annealing. Okay. Next. Our surface analysis, as shown by the XPS data on this slide, demonstrates the effectiveness of the PVA additive in mitigating oxidation. This shows that pure tin-based perovskite stirring overnight has high percentage of tin4+, which is 77.77% area, indicating significant degradation. In contrast, the left one shows that pure formamidinium tin iodide sample stirred for 2 hours is also degrade to the SN4+ at 56%. However, after we added PVA, the results were dramatically different. Let's see the bottom graph for the formamidinium with PVA. There's two kind of sample, 2 hours and overnight stirring. For the 2 hours, so much lower tin4+ area percentage, around 18.46%, and this is improved. The stability is even more evident to the right graph, where the overnight stirring is around 13%. This is clearly that PVA successfully slows down the degradation of tin2+ to the tin4+ on the surface. Okay, move to the next. We observe the similar trend in the bulk of the material. the hard XPS data of the left side, the left one shows that the pure formamidinium tin iodide sample 2 hours has tin 4+ area, which is 59%, which increased to the 66% to overnight sample. In contrast with the PVA, exhibit significantly less degradation. Formamidinium tin iodide with PVA for the 2 hour steering has tin 4+ around 9%, and the overnight sample is around 10%. This confirms that PVA successfully inhibits the oxidation of the tin 2+ throughout the bulk material. Furthermore, our analysis indicates the addition of PVA does not change the fundamental crystal structure, which is both are orthorhombic phase. Both sample either pure or with PVA additive show identical diffractional patterns. And also the PL graph show the the PVA sample has higher PL intensity compared to the pure one. This increased PL intensity is the key indicator of reduced non-radiative recombination within the material. The higher PL signals suggest that the PVA additive successfully pacificates defects in the perovskite film. So let's see to the table. There is the band gap of each are 1.48 electron volt to the
Excuse me,
pristine.
Rosnewa.
Okay.
You have 1 minute left.
Okay, these findings agree with the previous report. Okay, next. To optimize device structure without additive, we use SCAPS 1D simulation. This is how the SCAPS 1D simulation calculate the device structure. So we have an IP structure. There is FTO, ETL, formamidinium tin iodide, HTL, and electrode. Okay, next. So here's the analysis, how the result changed with variation of the ETL and HTL. The IV curve of a zinc oxide device showed a slightly higher VOC compared to the titanium dioxide and tin dioxide. And then furthermore, the EQE curves below demonstrate all materials have very similar spectral response across the visible range, which is above 80%. This indicates that these ETLs are highly effective generating charge carriers from photons for the tin-based perovskite. And then for the HTL, we test the wider range of many materials. We found that for PTAA and copper oxide and also copper peroxide have the stable fill factor. Most importantly, the final efficiency we plot the PTAA, P3HT, and CuSCN and copper oxide most highest efficiency. Our analysis reveals that the choice HTL materials has more pronounced impact on the device performance than the ETL's variation. Okay, next. Please move to the next slide. Okay, here we optimize the structure absorber layer itself. Okay. Our final simulation focused on the back contact. The graph on the left show that the work function various materials. We found that the back contact with work function of 5 electron volt or higher, such as gold or platinum, leads to efficient ohmic contact, which improves both VOC or and fill factor. And also the graph on the right, there is our final optimized device structure. The FTO, zinc oxide, tin-based perovskite, PTAA, and nickel, we were able to increase theoretical efficiency from 25% 4% as a lower limit to the 30% up as an upper limit. This demonstrates the significant potential for improving tin-based perovskite solar cells through careful device engineering. Okay. Next, for the conclusion, our research yields two key findings. There is effect of PVA additive to the formamidinium tin iodide and also simulation of formamidinium-based perovskite solar cells. These results is already submitted to the journal, and now the status are still under review. That's all from me. Thank you for your time and attention. I will return back to the chair, Ms. Adita.
Okay, thank you very much, Ocha, for the informative and inspiring presentation today. Wishing you success with your research. Now, let us continue to Q&A sessions. Okay, for audience, if you have any questions. Okay, we have one question here from Marisa Prasavitri. The question is, what inspection methods are effectively used for predictive maintenance on solar panels? And if there are any findings, please share the reference and type findings. Currently, I am conducting inspection using a thermal camera. Okay, Roshaila, please answer the question.
Yeah, actually, our simulation is only for the device perovskite solar cells. So,
I'm sorry, I think
can you
the question is out of the topic by Roshaila. So let's ask continue to another questions. All participants, if you have any question, please raise your hand. Okay, we have one question here from Mr. Wilman. Mr. Wilman, time is yours.
Okay, thank you, Ms. Ocha, for a nice presentation. So on the so you show a lower limit, top, upper limit, and practical simulation. Can you elaborate more about the differences among those three simulations?
Yeah, actually for the I can directly answer, Miss Adita. Okay, for these three kind of results as an optimized structure. So we have the upper limit. Upper limit with means that our variation of defects is higher, is lowest, and for the lower limit, the defect is highest. So for the practical, we have some data to compare with the experimental data, and there is prediction for the practical limit for the perovskite solar cell based on tin. So we have a lot of variation of defect, like defect of bulk, the perovskite, and the interface defect. So for any variation, we limited the range of the defects. Okay.
Okay, thank you very much for your answer, Mr. Shaila. And because we have the time is over, so we have to continue to the next speaker. Okay, thank you very much, Mr. Shaila, for your participation in our symposium. We really appreciate it. Please give applause to Ms. Shaila. Okay, now we are going to the next young scientist speaker, Muhammad Asarudin from Physics Department, Institut Teknologi Bandung. Mr. Asar will talk about absorption and photoluminescence characteristic of colloidal bianion cesium lead halide perovskite nanocrystal. Please welcome Mr. Asar. The screen is yours.
Well, thank you very much for this opportunity. Maybe I will share about my presentation. Okay. Ya, Assalamualaikum warahmatullahi wabarakatuh, and good morning, everyone. My name is Muhammad Sarodin. I'm from Institut Teknologi Bandung, and today I'm going to present our work about perovskite, and the title is the absorption and photoluminescence characteristic of colloidal bianion cesium lead halide perovskite nanocrystals. Okay, my presentation divided by 4 parts: the introduction, experimental result, and discussion, and summary. Okay, in recent years, the development of organic and inorganic nanomaterial semiconductor is growing rapidly. And one kind of materials is a perovskite. And maybe some of you are familiar about these materials, and the previous presenter has been mentioned it before, but I will explain a different type of the perovskite, which is all inorganic lead halide perovskite. Well, this material has attracted significant attention because the outstanding properties, including the tunable band gap, high light photoluminescence, quantum yield, narrow emission bandwidth, high color purity, and covering of visible light energy. We're just making them as a promising candidate for optoelectronic devices like solar cell, LED, photodetectors, and photocatalysts. Okay, in our previous work on cesium lead bromide nanocrystal from the band structures and projected density of state calculation, we confirmed that this material has a direct band gap, and the valence band maximum is primarily composed of the BR4P, while the conduction band minimum is mainly derived from the PB6P orbitals. And based on this theoretical calculation, we can project that this material has a strong optical transition and efficient photoluminescence properties. Experimentally, we also confirmed that this material has a high chiral intensity with efficient band edge combination. And our work, we have clarified that how the molecule organics and the surface state can affect the photoluminescence properties of these materials. So based on these findings, it can give us a knowledge about our current work to optimize their application by the tuning optical properties like the emissions wavelength. So the big question of our work is the how to tune the optical properties of this material, especially the emissions wavelengths. So generally there are 3 strategy of to tune this perovskite to tune the emission spectrum of this perovskite materials. And among this strategy, the halide compositions, we focus on the halide compositions, where this strategy give us a simple and straightforward way to modify the optical properties of these materials. And by mix the halide anions, we can control the band structure, which is, as I mentioned earlier before, that the band structure is component the PB4P and FBR6P and anion halide. So it can affect the wavelength emission, then the absorption. So it can extend the wavelength range for the all inorganic perovskite solar cells. So in this study, we investigate the influence of bromide and iodide ratio in mixed halide perovskite nanocrystal on their optical properties with respect to the nanocrystal size and the electronic structure for the optoelectronic application. Okay, for the experimental, we use wet chemical process where we use hot injection to prepare the cesium lead bromide, cesium lead halide nanocrystals, and first we prepare the cesium OLED and the PbX2 was dissolved in the octadecene and oleamine and oleic acid as a ligands, and followed by the rapid injection of the cesium OLED to obtain the nanocrystal. And for the mixed halide, we can introduce the PbI2 with the difference with the difference ratio, and by introduce the PbI2 we can form the mixed halide perovskite, and after that we continue to this to the next treatment like centrifugation and purification to remove the residuals from our nanocrystals, our colloidal nanocrystals. And for the characterization, we use several characterization. So for the structural and morphological, we use XRD and HR time. And for the optical properties, we use a UV spectroscopy, VL spectroscopy, and VL decay measurement. And first, I'm going to explain about the cesium lead bromide nanocrystal in the structural and morphological property. And the XRD in the left one is the XRD pattern of the cesium lead bromide nanocrystal, and the diffraction peaks is matching well with the reference, and confirm these nanocrystals has a thorambic crystal structure. And the right one is the TEM image of the cesium lead bromide nanocrystal, and the TEM image reveal that the uniform nanocubes with the relatively narrow size distribution, which is indicating that a good morphological control on the nanocrystal or the colloidal nanocrystals. And for the next is we compare the cesium lead bromide nanocrystal and the cesium lead iodide nanocrystals. The TEM image of cesium lead bromide crystal on the left, and the right side is the cesium lead iodide nanocrystal, and both of them exhibit this nanocubic shape morphology. But in the cesium lead iodide nanocrystal, it's shown a larger nanocrystal size compared to the cesium lead bromide nanocrystal, which can be explained because the iodide anion radius of the iodide anion has a larger rather than bromide anions. For the mixed halide nanocrystal, we can see that the HR10 show the increasing of the nanocrystal size from the 90.56 nanometers from the to the 15 nanometers, where the increasing nanocrystal size with the increasing the more iodide content, it is is due to the larger ionic radius of iodide, leading to the lattice expansion and larger nanocrystal size. To investigate the optical property of this nanocrystal, we performed the absorption and photoluminescence spectroscopy, and we found that the both of the absorption and the photoluminescence show the progressive redshift as iodide iodide content increase, and where the pure bromide perovskite emits around 570 nanometers and 7 nanometers, and the pure iodide around 696 nanometers. And this gradual shift indicates that we can precisely control the emission color of this nanocrystal by adjust the halide ratio. For further, we also calculate the optical band gap using touch plot analysis, where we found that the cesium lead bromide nanocrystal show the largest band gap, around 2.39 electron volts, while the cesium lead iodide has the smallest band gap. And we can see that as the iodide content increase, the optical band gaps the optical bandwidth are decreased. This is caused by this reduction is also correlated with the larger nanocrystal size, and showing that both the halide composition and nanocrystal size govern the optical properties. And for
Excuse me,
further
Asar, you have 2
investigation,
minutes left.
we also measure the
Excuse me,
PLDK
Asar,
for. Yes.
you have 2 minutes left.
Okay, thank you. We perform the PLDK and we fit by the B exponential function, and we excited and we can get the two components, the fast decay and slow decay component, which is represent the two type of the recombination pathway. So for the pure cesium lead bromide nanocrystal, we can see the cesium lead bromide has a shorter decay component rather than the cesium lead iodide component. It can be explained because the cesium for the cesium lead bromide nanocrystal, the exciton may be more confined due to the larger band gap and the smaller nanocrystal size, which is indicating that radiative recombination is primarily occurs on the internal state of the nanocrystal, with the less influence from the surface related. On the other hand, the cesium lead iodide has smaller band gap and the larger nanocrystal size, which is reduce the quantum confinement. As a result, the surface related state will influence the recombination pathway. So we can get it. The cesium lead bromide has cesium lead iodide has a longer compared to the cesium lead bromide nanocrystal. So for the mixed halide nanocrystal, we obtain several different phenomenon. In a mixed halide process, this component correspond to the excitonic recombination occurring at different local halide environment. Some sites are more BR rich, and some sites and the others are iodide rich. As iodide content increase, you can see the decay shown are very long. It can be explained that the fast decay component in the first one is a rapid. It's represent the rapid energy transfer from the bare rich region to the iodide rich region, and the second one is a sixton division within the lower energy domains before undergoing radiative recombination. For the summary of our work, the mixed halide peroxide nanocrystal was successfully tuned to the control the optical properties of the nanocrystal, and by increasing the iodide content, it can be cause the larger nanocrystal size, which reduce the quantum confinement and resulting in the redshift of the absorption and the PL spectra, indicating narrower optical gaps. And this work may be insightful for the development of the active material to expand the wavelength absorption of the all inorganic perovskite solar cell. Thank you very much.
Okay, thank you very much, Asar, for your excellent presentations, and congratulations on your achievement in your research. Let's continue to Q&A sessions. Okay, for audience, if you have any questions, please raise your hand or write in the chat box. Okay, we have one question here from Miss Lia Yuliantini. Okay, thank you for your interesting presentation, Mr. Asar. I have a question. What is the typical excitation wavelength used to probing the sample, and over what spectral range can the emission be tuned by mixed halide perovskite composition or method that you used? Okay, Asar, please answer the question.
Okay. For the excitation wavelength, we use the laser. We use laser, and typically the wavelength is 420 nanometers, and we use the MPD detectors for collecting the photoluminescence of our sample and for the okay. And okay, for the spectral range, we okay. To tune the optical properties of our nano crystal, we use hot injection method where we adjust the halide composition, bromide and iodide from the PbX2 salt, and we adjust the ratio, and so we can obtain the several spectra of absorptions and photoluminescence, and it can be shift to the longer wavelengths as iodide content increasing. I think so.
That's all.
That's all my answer.
Okay, thank you for your clear answer. We have two questions more here. Second one from Mr. Willman. The question is, have you ever tried to synthesize? Okay, I think one question because the limited time.
Okay.
We choose one question from Mr. Willman. The question is, have you ever tried to synthesize this pure perovskite, for example, CSPB2BR5, and observe its PL in comparison to the pure one? Okay,
Okay.
Asar, please answer the question.
Okay. Actually, I have tried to synthesize the cesium pure perovskite, and we confirm these structures from the XRD and the XPS analysis, where the photoluminescence it's very low. It's very low because we found that's not only the single phase of the cesium lead bromide, but also in the cesium PB2BR5 phase. So the PL properties of this cesium pure perovskite, it's lower than the cesium lead bromide nanocrystals. I think that's all.
Okay, thank you, Asar, for your answer. Unfortunately, we are running out of time for Q&A session, and we apologize because we cannot answer all the questions. But Asar, you can answer the question in the chat box. Thank you very much for your participation in our symposium. Please give applause to Muhammad Asaruddin. Okay, now we are continue to the next distinguished speaker, Professor Akihiko Fuji from the Osaka Institute of Technology, Japan. Before we begin, let me introduce Professor Fuji's background.
Sorry.
Yeah. Professor Akihiko Fuji received the bachelor, master, and doctoral degrees from Osaka University in 1993, 1995, and 1997, respectively. After a one-year GSPS fellowship, he joined the Department of Electronic Engineering at Osaka University as a research associate in 1998, and was later promoted as to associate professor in the Division of Electrical, Electronic, and Information Engineering, Graduate School of Engineering, Osaka University in 2006. He is currently a professor in the Department of Electrical, Electronic System Engineering, Osaka Institute of Technology. His research has focused on optical and electrical devices utilizing organic materials, including dye-molecule and conducting polymers. He is also an active member of several academic societies in Japan. Today, Professor Fuji will deliver a presentation entitled Uniaxial Coating for Inorganic Halide Perovskite Thin Films and its Solar Cell Applications. Now, let us warmly welcome Professor Akihiko Fuji. Professor Fuji, the screen is yours.
Thank you very much for your kind introduction. I'm Akihiko Fuji from Osaka Institute of Technology, Japan. First, I'd like to appreciate organizers to give me an invitation to this symposium, particularly the Dr. Adita Smanumiza. It's a great honor for me to have invited talk here. Today, I'd like to talk about the recent work of perovskite solar cell with uniaxial coating technique. Before my talk, let me introduce my place, Osaka. Osaka is located on the west part of main island, Honshu, Japan, and between Kyoto and Kobe. In Osaka City, Expo 2025 is now held in the Bayside area. Many visitors from abroad are coming there, and or Universal Studios Japan. Our university is located on the opposite side, northeast area of the city. It's a little bit small campus, but a very beautiful riverside location. So if you have chance to come to Osaka, please visit us. Okay, this is outline of my talk today. First, I mention about the research background, then explain about the characteristics of perovskite bar-coated thin film, including solar cell performance. Then I demonstrated 2D, 3D perovskite heterostructure by dual bar coating technique. Finally, I will summarize my talk. This is a similar slide about the background of the perovskite, but I explain again. As you know, the inorganic halide perovskites have recently attracted much attention because of some advantages for their application. This kind of perovskites consist of organic cation, and halide anion, and MaPbI3 is well known as a representative material. Their solution processability is one of the most important characteristics towards practical thin film production by printing process. This material exhibits outstanding photoelectric properties such as absorption coefficient and spontaneous charge separation and long charge diffusion length. So the material being considered for the variety of photoelectric devices. In particular, it effectively works as active layer of the solar cell and exhibit a high power conversion efficiency exceeding 27%, which is comparable to the silicon-based solar cell. So many researchers studies on the photovoltaic solar cells, and lots of companies all over the world were developing the products as a next generation solar cell. Perovskite thin film can be fabricated by a solution process because of the solubility of the precursor material. In actual spin coating, many researchers, so former presenter also using spin coating method, is very available for fabricated thin film very easily. In this method, perovskite precursor solution is dripped onto the substrate. Then the substrate rotated at high speed for a minute. During the rotation, poor solvent must be additionally dripped onto the substrate to promote the chemical reaction and obtain the uniform film. However, this method is not so appropriate for a large area production, and it has some difficulty to drip the poor solvent precisely. So another solution process should be studied for the large area production, such as printing process, including inkjet or braid coating and so on. In this study, we focus on the very simple but fundamental technique about coating method, like that. The bar coating is a simple way, but the essential printing method to realize a uniform and large area thin film and to avoid material loss. Therefore, our work should be a basis of a practical technique towards the industrial mass production. In barcoding method, many parameters exist, control the film thickness and film quality. For example, solvent and solution concentration, substrate materials and their wettability, coating bar material and their surface shape, gap distance between the coating bar and substrate, coating bar sweep rate, substrate temperature, and so on. So many parameters exist. So it's a little bit complicated to determine the optimal condition. But in order to obtain the high quality films in our study, we especially focus on the additive material in the precursor solution, coating bar sweep rate and the substrate temperature. The other parameters fixed to be constant. Okay, I briefly explain about some important results in the characteristics of MAPBI3 bar-coated thin film. This slide shows the typical fabrication procedures of thin film and solar cell in this study. ITO and whole transport layer, PSS coated substrate was prepared. Then perovskite layer, MAPBI3, was coated by the bar coating. This movie demonstrates actual bar coating by our homemade coating machine. The coating conditions are shown here. Ammonium chloride was used as additives of the precursor solution. DMSO is used as a solvent, and precursor concentration is fixed to be 1.3 molar. The typical substrate temperature was kept at 100 degrees C, and the coating bar speed was controlled between 200 to 4,000 micrometer per second. Very, very slow. For completing the solar cell, electric transport layer of PCBM and counter electrode of silver were also fabricated. Here we discuss some notable topics, namely large grain formation, additive effect, and sweep rate dependence of the film thickness, and device structure modification of solar cell. Okay, first large grain formation and additive effect. Comparing with the conventional spin coating film by SEM observation, surface morphology are completely different each other, as you see. In the case of spin coating, the film seems to have a smooth surface macroscopically, but so many grains could be seen in the same image. On the other hand, the grain size 1 to 2 micrometer at most. On the other hand, such a small grain could not be found in bar-coated film, and the surface seems to consist of large crystallite. The grain size is estimated to be 40 to 100 micrometer. That is, large size grain can be obtained just using bar coating technique. From the XRD patterns, spin-coated film exhibit some diffraction peaks based on the randomly oriented MAPBI3 microcrystals. On the other hand, the plane orientation 200 or 400 of MAPBI3 was vertically aligned in the bar-coated thin film. That is MAPBI3 thin film with a highly oriented crystal axis was successfully obtained by our bar coating method. The large size grains were realized indeed, but the film surface was not so smooth like that. That should be a problem like contact resistance, leak current site, or carrier trap site in solar cell devices. In actual, the series resistance was too high, and voltage loss can be recognized from the open circuit voltage. Additive material into the precursor solution sometimes plays an important role to improve the film quality. Here, we use ammonium chloride as an additive material and dissolved into the precursor solution. Then film surface became very, very smooth. In the JV characteristics, the series resistance was suppressed, and PCE of the solar cell was markedly improved. The detailed mechanism is still not so clear, but according to the report literature, ammonium chloride was weakly combined with precursor materials to form the intermediate media. Then MAPBI3 crystal grows up, removing ammonium cation and chloride anion. Therefore, it is suppose that ammonium chloride slightly disturb the crystal growth of MAPBI3, resulting in the appropriate growth rate to form a smooth surface. Such an additive effect might be explained in this slide. This is a case without ammonium chloride. The nucleation of MAPBI3 occurs on the substrate, and island shape crystal grows up three-dimensionally. And some delayed nucleation also occurs sequentially. Small time difference of the nucleation influence the surface uniformity. On the other hand, with ammonium chloride, it is considered that intermediate medium formation delays the nucleation perovskite. So it is considered that the balanced rate of nucleation and crystal growth was realized. Thus, the smoothness and uniformity can be improved. Okay. Okay, let's move on the sweep rate dependence of the film thickness. The film thickness is one of the important factors for solar cell, as you know, and it can be confirmed from the cross-sectional SEM image. As you can see in these images, surface is very flat and smooth. It's okay, and film thickness depends on the sweep rate of the coating bar, okay, 200 micrometer second to 4,000 micrometer second per second. Plotting the film thickness against the sweep rate, it is noted that data plots fitted two lines like that. So the separated two regions seems to exist. One of them is proportional to the minus 1.19 power of the sweep rate in the slow region. And the other is proportional to 0.60 power of the sweep rate in the relatively fast region. The relationship between the film thickness and sweep rate is schematically explained using two regimes. When the sweep rate is very low, it is called evaporation regime. The chemical reaction from the precursor to MAPBA3 is simultaneously promoted just after coating. On the other hand, when the sweep rate is relatively high, it is called Randall-Levitch regime. Substrate is completely covered with a precursor solution by coating. This is the first step. Then the chemical reaction and crystal growth occur by giving thermal energy or promoting solvent evaporation. This is the second step. Theoretical equations were proposed for the evaporation and Randall-Levitch regimes in this literature about the braid coating of the phosphatide. The thermal process is needed in the case of the MAPBA3 film formation, but the theoretical relationship were also adaptable to the bar-coated thin film of the MAPBA3. In this study, the intermediate condition around here, around 1,000 micrometer per second between the two regimes was distinguished and called as a transition regime. In this slide, let me compare the film fabricated three regime conditions by using the same images. Using the evaporation and transition regime, it's effective to improve the surface roughness. In Randall-Levitch regime, many voids appeared. In the XRD patterns with out-of-plane condition, marked 200 peak, 200 orientation can be confirmed in all regimes. The relatively narrow peak can be found in the transition regimes and Randall-Levitch regimes. That indicates a high crystallinity. The locking curve measurements also carried out for checking the precise orientation angle of the crystal axis. 200 crystal axis completely aligned to the vertical direction of the substrate for all films. Narrowest peak can be clearly seen in the transition regime condition. Thus, the transition regime condition is likely to induce the highest crystallinity in these three regimes. This slide shows the solar cell performance in each regime. In the evaporation regime, fill factor was large due to the relatively small series resistance based on the suppression of the surface roughness. In the Randall-Levitch regime, relatively large VOC was achieved. The high crystallinity might be one of the reasons. In the transition regime, short circuit current was a little bit reduced due to the relatively low film thickness but the fill factor and the open circuit voltage were better due to the combination of both features of evaporation and random Levitch regimes. Then the maximum PCE of 14% was achieved in this experiment. Such a sweep rate dependence of film thickness was also confirmed in another perovskite thin film fabrication. This is one of the examples. Triple cation type perovskite, including cesium cation. The similar V-shape characteristics appears in the sweep speed dependence of the film thickness. And film thickness can be controlled by sweep speed of the coating bar. Okay, so for achieving the higher PCE, appropriate materials for carrier transport layer and device structure should be carefully selected from the candidates. Many kinds of materials and device characters were proposed in the previous reports. For example, as whole transport layer candidate material, PSS, PTAA, Spiro, TDA, and so on. Some other materials, such as dopant-free molecules, are also the candidates. As electron transport layer material, semiconductor oxide, titanium oxide, zinc oxide, and fluorine derivative, PCBM, were often used. Two typical device structure of normal and inverted type were widely studied. In this study, tin oxide was adopted as an electron transport layer in normal type device structure because energy level matching with the perovskite as well as high transparency, low temperature processability. Using the tin oxide as an electron transport layer in normal type solar cell, crystallinity of the MAPBI3 bar-coated film was also improved. That is effective for the separation of the interface recombination, resulting in the enhancement of JSC. Because of the electrode combination with gold electrode, open circuit voltage was also enhanced in comparison with the inverted type solar cell with P.PSS whole transport layer and the silver electrode. Consequently, 16.8% of PCE was achieved at present. Okay, next, I demonstrated 2D, 3D perovskite heterostructure by dual bar coating. MAPBI3 is the most famous material in perovskite solar cell, but possesses a fatal disadvantage, namely low stability and atmospheric environment. Especially the water molecule easily reacts with perovskite, resulting in its degradation. As one of the solutions for this problem, the use of 2D nanostructured perovskite is proposed as a passivation layer material because the continuous organic cation layer prevents from the water molecule diffusion into the perovskite lattice. Therefore, the realization of 2D, 3D perovskite heterostructure must be significant for the solar cell stability. This is one of the hot topics in this field. Such heterostructures can be roughly classified by two types, horizontal and vertical types. Taking the photogenerated carrier transport into consideration, vertical type must be suitable for the solar cell application. But most of the reported heterostructures are based on the horizontal type, and uniform fabrication of vertical type heterostructure has not been reported before. So we propose a dual bar coating for 2D, 3D perovskite heterostructure as following. At the first bar coating, 200 oriented 3D perovskite was prepared, as I mentioned before. We expect that the uniform orientation of 200 behave as a template of the vertical 2D perovskite. At the second bar coating, a solution including another organic cation, butyl ammonium cation, was coated at 80 degrees C with the same sweep rate. In this process, methyl ammonium cation in 3D perovskite are exchanged with butyl ammonium cations during the second bar coating. The total thickness never changed, but 2D, 3D heterostructure remains after solvent evaporation. For confirming the heterostructure, peer photoluminescence measurement is adopted. Peer measurement is one of the valid methods to confirm the 2D, 3D perovskite heterostructure because peer photoluminescence spectra changed when the excitation light was irradiated from the film surface side or substrate interface side. Two peaks due to the quantum size effect of the 2D perovskite can be found at 600 nanometer from the surface. They should be corresponding to the low number 2D perovskite. In the case of the excitation to the substrate interface, only the peer photoluminescence from 3D perovskite was observed. Judging from these results, the 2D perovskite layer exhibits only near the film surface. Thus, 2D layer thickness can be roughly controlled by adjusting concentration of butyl ammonium solution. The orientation, okay.
Excuse me, you have 5 minutes left.
Okay, thank you. The orientation of 2D perovskite was investigated by using GI wax technique. This 2D diffraction pattern indicates the 2D perovskite was obliquely aligned at 45 degrees to the substrate surface. It is not perfect vertical orientation, but it should be sufficiently effective for the carrier transport. If another template 110 oriented 3D perovskite film is used, horizontal orientation can be also fabricated. It's not appropriate for solar cell, as I mentioned before, but it might be useful for some other application like light emitting devices. Thus, the 2D perovskite orientation can be partly controlled by using 3D perovskite as a template. This is an example of the solar cell performance in comparison with the 3D perovskite MAPBI3 solar cell. Since the 2D perovskite layer is quite thin, the JB characteristics is almost the same with the 3D perovskite solar cell. It is considered that the 2D perovskite layer does not disturb the carrier transport. Investigating a time dependence of the device performance, PCE, the market high device stability can be found in 2D, 3D heterostructure solar cell. 2D perovskite is effectively working as a passivation layer as well as a carrier transport layer. Okay, let me summarize my talk. The thin film on MAPBI3 with high quality was successfully realized by adopting bar coating process. And the relationship between the thickness, film thickness and sweep rate was investigated. And the typical solar cell with MAPBI3 thin film demonstrated PCE of 16.8% in the case of the transition regime. Orientation control to the perovskite on 3D perovskite in the heterostructure was realized by template growth technique. Okay, finally, I'd like to say thanks all my colleagues and collaborators, particularly Professor Rahmat Hidayat and Dr. Aditya Nizar for carrier transport and defect state studies. This work was financially supported by some grant as shown here. Thank you very much for your kind attention.
Okay, thank you very much, Professor Puji, for your informative and inspiring presentation. We truly appreciate the insight you share on uniaxial coating and its application in perovskite solar cell. I find this technique particularly interesting as it allows control over the growth direction, and it represents a promising alternative that could be applied for upscaling solar cell. Anyways, long time no see, Sensei. How are you? Okay, let's continue to the next session, Q&A session.
Yep.
We have one question here.
Thank you.
Two questions. Okay, first question from Mr. Yuliar Firdaus. The question is, thank you, Fuji Sensei, for this nice talk. I have a question about vertical type 2D perovskite in terms of charge transport. I can imagine it's probably will be more favorable compared to the horizontal type. Is that correct? Also, how about stability? Is the vertical direction to the perovskite going to sacrifice the long-term stability due to less protection from organic molecule in the 2D perovskite?
So questions stability. Yeah.
Okay, Sensei, you can answer the question directly.
Yeah. So now we didn't succeed perfectly the vertical alignment orientation. But we think this type of inclined type to the perovskite is maybe enough. We didn't check the carrier transport, carrier mobility or some conductivity because the very thin film or very thin layer. So it's not so clear, but so from these results, we judged this kind of to the layer to the perovskite layer is well working, we think. But okay, so what's a question point? Sorry, is it enough answer?
To Mr. Yuya, is it clear enough?
So if you need some more information, I can say something more. Yeah, we control the to the perovskite layer. I just showed the butylammonium cation case, but we have longer chain cation, and we tried them And if the lattice matching, sorry, okay, here. If the lattice matching is very well, this kind of vertical or inclined alignment is realized. But if lattice matching is not good, to the perovskite layer is not so good working.
Okay, Sensei, thank you very much for your answer. Let's move to the next questions. We have two questions here. For the second one is from Mrs. Natalita. Time is yours.
Thank you, Ms. Adita. And thank you, Prof. Akihiko, for your very insightful presentation, very interesting presentation.
Yeah.
I think the bar coating method that you presented is very interesting because it's quite new, I think. I haven't seen any this technique before. I mean, the most popular technique, I think the most popular technique is actually plate coating, right? Usually people use plate coating or spin coating. And I'm just wondering if you've done any study on comparing the crystallization behavior for the perovskite layer if we use plate coating versus this bar coating. And then my second question is, have you done any study to analyze the effect of solution concentration or solution, the viscosity of the solution that you use in this bar coating method? And if so, do you have any suggestion on the ideal viscosity or the ideal concentration if you want to use your technique, the bar coating technique? Is it the same like the solution viscosity that we use if we use spin coating method or plate coating method? Thank you.
Okay, thank you very much. Sorry. Okay, so first question, the difference between the bar coating and blade coating. Maybe important point, yeah, in your case, very, very slow sweep speed in the coating. Maybe the similar coating speed, the most important point, meniscus. So maybe meniscus from the substrate, meniscus part of the film. So we essentially the blade coat and bar coating is similar, almost similar, I think. So okay, I showed this slide. We studied okay. We studied this literature before our barcoding study, barcoding research. So it's a very, very similar V-shape characteristics. So maybe in principle, the bar coating and blade coating are quite similar. And second question, okay, is maybe you have an interest about the condition of the coating. Yeah, I mentioned before that there are many, many parameters. We didn't check the viscosity, but I think a very important point, because if the viscosity is changed, film thickness also changed if we use the same other conditions. So in that case, but not so. In your case, the viscosity is almost a constant, and then another parameter was checked in this stage. Okay,
Okay, thank you, Professor.
thank you.
Okay, thank you very much, Professor Fuji, for your clear answer. And we have the third question here from Ms. Lia Yuliantini. The question is, thank you for your insightful presentation, Professor. I have a question regarding the bar coating process. Is the gap between the sample and the coating bar maintained at a constant distance during the deposition? Additionally, it's possible to apply the bar coating method for depositing other functional layers, such as the electron transport layer or carbon-based electrode. Sensei, please answer the question.
Sorry, I missed the final point. So you mean say electrode also to form this technique? Sorry.
You can continue your answer, Sensei.
Yeah, please repeat the question, last part of the question, please.
Oh, okay. Is the gap between the sample and the coating bar maintained at a constant distance during the deposition? Additionally, is possible to apply the bar coating method for depositing other functional layers, such as the electron transport layer or carbon-based electrode?
Yes. If the okay, yeah, okay. I showed this is a fabrication process. Of course, we try to make a PEDOT PSS layer and PCBM layer by using bar coating. But yeah, so it's a similar results was already obtained. So it's possible. And coating bar height is almost a fixed 700 micrometer from the substrate. Is it enough for the question?
Mrs. Lia, is it enough?
Enough, Professor. Thank you very much for your answer.
Yes, sorry. Thank you, Sensei, for your answer. Okay, we have one more questions for Mr. Gerald. The question is, thank you, Fuji Sensei. I want to ask about the charge transport properties of the large grain size perovskite, because grain boundary usually attribute to trap state and hysteresis. In your case, can you see direct effect of the grain size on the electron hole transport properties, and how big is it improved as compared to the conventional small size grain? Okay, Sensei, time is yours.
Yeah. So I just can you show you maybe this, right? Yeah. In our experiment, so this is a forward scan and reverse scan overlapping. So hysteresis is very small in the bar coating method. So Yeah, it's barcoding is effective for the hysteresis less performance, I think. So because of the we think crystal or film defect is suppressed. It's effective, I think.
Okay, Sensei, I think your response is very clear. So, okay. Okay, thank you very much, Fuji Sensei, for your presentation today. And I will try to summarize your talk today. Professor Fuji Sensei present advance in fabricating high quality perovskite thin film using scalable uniaxial bar coating process. And this method enable large grain, well-oriented thin film with improved uniformity. The coating speed was shown to strongly influence film thickness and crystallinity, with the transition regime yielding smooth surface and efficient solar cell. Moreover, dual bulk coating enabled formation to D3D perovskite heterostructure with control orientation, achieving improved stability and charge transport. This result highlight bulk coating as a practical pathway towards scalable, stable, and high-performance perovskite solar cell. Thank you very much, Professor Fuji, for sharing your expertise with us today. I hope we will have the opportunity to collaborate again in the future. Wish you all the best for the future. And we also thank you all participants for your thoughtful questions and active engagement. And this is the end of the sessions. We will now take a lunch break, and please return to the Zoom meeting at 1:30 p.m. GMT +7 for the next agenda. Wassalamualaikum warahmatullahi wabarakatuh.
Research Center for Electronics is part of the Research Organization for Electronics and Informatics at BRIN. The Research Center for Electronics, or RCE, is home to 8 research groups that work together to explore new ideas, develop innovative tools, and contribute to national development through electronic science and technology. Advanced Photovoltaic and Functional Electronic Devices Research Group is one of the research groups in RCE, which specifically focus on the development of photovoltaic and functional electronic devices technology using novel semiconductor materials and the optimization of their fabrication process to obtain highly efficient devices. The objectives of this team are: 1. To bring together a multidisciplinary research team. 2. To be the center of excellence for research and innovation in the field of advanced photovoltaic and functional electronic devices technology. 3. To achieve balance between high-quality science and practical technology as the main research output. This research group is located in KST Samaun Samadikun, Cisitu, Bandung, Indonesia, which is known to be the home of Advanced Semiconductor Device Fabrication Center. At BRIN KST Samaun Samadikun Bandung, a wide range of state-of-the-art photovoltaic device fabrication and characterization facilities are available to support the research and development activities. Together, we aim to build technologies that are not only advanced, but also meaningful and impactful. Electronics is a key area of science and technology that supports many aspects of modern life. In this research group, we believe that the development of advanced photovoltaic and functional electronic devices are essential as the building blocks for determining innovative electronics technology in the future. We also believe that collaboration is central to our work. Therefore, any future collaborations are always welcomed.
high-sensitized solar cell is one of the newest third-generation solar cell technology. Just like photosynthesis in plants, DSSC uses dye molecules to absorb light and then convert them into electricity through photoelectrochemistry. The key benefits of DSSC modules are clean and sustainable. The DSSC in this innovation runs on solar energy, which provides clean, endless power since it is the most abundant source of energy in the universe. So you will never run out of energy as you can charge anytime, anywhere, wherever there is light. Affordable. DSSC module uses much cheaper materials than the conventional crystalline silicon-based solar panels. DSSC can also be produced using simple processes in a typical lab without the need of high vacuum equipment. Flexibility. Unlike conventional PV, DSSC not only works under direct sunlight but also works under artificial light indoors and even on cloudy days. It can also be made in various sizes, colors, transparent, and even flexible. Integration. DSSC can be applied in building integrated PV, providing energy in smart buildings, yet with an aesthetic visual. It can also be integrated into IoT and electronic devices and various smart gadgets in your daily life. The integration opportunities for DSSC are endless. DSSC, a device that charges with light, not only better for you, but also for the environment.
Perkenalkan, nama saya Sorel Mono dan saya salah satu peserta riset asesmen di sini. Dan yang saya sekarang meneliti tentang sel surya. Ayo kita sama-sama. Jadi sel surya, karena kita hidup di negara yang lebih tropis yang memiliki matahari 12 jam, jadi kita harus meneliti mengenai sel surya atau device yang dapat menghasilkan energi listrik dari cahaya matahari. Nah, yang kebetulan untuk saya sendiri itu riset tentang material dari si sel surya tersebut, yaitu material perovskite yang tapi lebih spesifiknya itu menggunakan inorganic perovskite solar cell. Yuk, kita biar tahu cara bikin solar cell.
Step pertama adalah untuk mengambil prekursor dari glove box dengan hati-hati karena prekursornya sangat rentan terhadap oksigen, sehingga harus di-store di dalam glove box sehingga diambil. Nah, setelah diambil, step berikutnya adalah untuk mendeposisi prekursor kepada substrat sehingga menghasilkan lapisan-lapisan sel surya tersebut. Dideposisikan menggunakan spin coater. Untuk caranya adalah untuk meneteskan beberapa tetes dalam substrat kemudian di-spin sehingga menghasilkan sebuah lapisan tipis. Kemudian lapisan-lapisan berikutnya dideposisi dan juga dipanaskan di atas hot plate untuk membentuk film tipisnya. Step terakhir adalah mendeposisikan lapisan kontak, yaitu menggunakan karbon, sehingga akhirnya terbentuk sel surya yang nanti akan diuji dengan menggunakan solar simulator.
Gimana kalian semua setelah melihat ini? Apakah tertarik mengikuti program Research Assistant? Jika tertarik, klik di bawah sini. Dan kalian bisa mendapatkan banyak ilmu dan pengalaman dari periset-periset di BRIN.
Kawasan Sains dan Teknologi Samaun Samadikun Bandung, sebuah pusat inovasi dan riset unggulan di Indonesia. Di sini, masa depan ilmu pengetahuan dan teknologi dirancang dan dikembangkan melalui fasilitas mutakhir dan aktivitas riset yang beragam. Di kawasan ini terletak laboratorium riset terpadu kami, tempat di mana periset dari berbagai disiplin ilmu bekerja sama untuk memecahkan tantangan kompleks. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun dilengkapi peralatan canggih yang mendukung riset dalam bidang informasi, komunikasi dan teknologi cerdas, memperkuat sektor transportasi dan teknologi lainnya. Riset kecerdasan buatan, mekatronika dan elektronika di sini mendasari pengembangan teknologi masa depan, memungkinkan Indonesia bersaing dengan sistem artificial intelligence global. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun juga menjadi pusat riset kegempaan, pemetaan sesar, tsunami, gerakan tanah, serta kajian risiko dan resiliensi bencana untuk mengurangi dampak bencana geologis. Selain itu, riset iklim dan atmosfer yang dilakukan mendukung mitigasi bencana alam, pengelolaan lingkungan, dan pencapaian tujuan pembangunan berkelanjutan. Fasilitas pengujian untuk memastikan bahwa teknologi dan produk baru memenuhi standar kualitas dan keandalan yang tinggi. Di kawasan ini, tempat di mana ide-ide baru lahir. Kolaborasi antara periset, industri, dan mitra internasional menciptakan solusi inovatif yang berdampak luas. Selain itu, kawasan ini dilengkapi dengan coworking space yang dirancang untuk menciptakan lingkungan kerja yang produktif dan kolaboratif bagi sivitas BRIN dan para kolaborator. Fasilitas di kawasan ini telah memenuhi standar pelayanan publik, mencakup tempat ibadah, parkiran, dan toilet khusus disabilitas, tempat menyusui dan daycare, kafe, serta fasilitas kebugaran baik di luar maupun di dalam ruangan. Kami juga menyelenggarakan seminar, workshop, dan pelatihan untuk meningkatkan keterampilan para periset dan SDM pendukung riset, serta berbagi pengetahuan terbaru dengan masyarakat. Kawasan Sains dan Teknologi Samaun Samadikun Bandung adalah salah satu bentuk komitmen BRIN untuk memajukan ilmu pengetahuan dan teknologi di Indonesia. Dengan fasilitas modern dan aktivitas riset yang beragam, kami bertekad untuk menciptakan dampak positif melalui inovasi. Bergabunglah bersama kami dalam merancang masa depan yang lebih baik melalui riset dan teknologi. Kawasan Sains dan Teknologi Samaun Samadikun Bandung, di mana ilmu pengetahuan dan inovasi bertemu.
Research Center for Electronics is part of the Research Organization for Electronics and Informatics at BRIN. The Research Center for Electronics, or RCE, is home to 8 research groups that work together to explore new ideas, develop innovative tools, and contribute to national development through electronic science and technology. Advanced Photovoltaic and Functional Electronic Devices Research Group is one of the research groups in RCE, which specifically focus on the development of photovoltaic and functional electronic devices technology using novel semiconductor materials and the optimization of their fabrication process to obtain highly efficient devices. The objectives of this team are: 1. To bring together a multidisciplinary research team. 2. To be the center of excellence for research and innovation in the field of advanced photovoltaic and functional electronic devices technology. 3. To achieve a combined balance between high-quality science and practical technology as the main research output. This research group is located in KST Samaun Samadikun, Cisitu, Bandung, Indonesia, which is known to be the home of Advanced Semiconductor Device Fabrication Center. At BRIN KST Samaun Samadikun Bandung, a wide range of state-of-the-art photovoltaic device fabrication and characterization facilities are available to support the research and development activities. Together, we aim to build technologies that are not only advanced, but also meaningful and impactful. Electronics is a key area of science and technology that supports many aspects of modern life. In this research group, we believe that the development of advanced photovoltaic and functional electronic devices are essential as the building blocks for determining innovative electronics technology in the future. We also believe that collaboration is central to our work. Therefore, any future collaborations are always welcomed.
Dye-sensitized solar cell is one of the newest third-generation solar cell technology. Just like photosynthesis in plants, DSSC uses dye molecules to absorb light and then convert them into electricity through photoelectrochemistry. The key benefits of DSSC modules are clean and sustainable. The DSSC in this innovation runs on solar energy, which provides clean, endless power since it is the most abundant source of energy in the universe. So you will never run out of energy as you can charge anytime, anywhere, wherever there is light. Affordable. DSSC module uses much cheaper materials than the conventional crystalline silicon-based solar panels. DSSC can also be produced using simple processes in a typical lab without the need of high vacuum equipment. Flexibility. Unlike conventional PV, DSSC not only works under direct sunlight but also works under artificial light indoors and even on cloudy days. It can also be made in various sizes, colors, transparent, and even flexible. Integration. DSSC can be applied in building integrated PV, providing energy in smart buildings, yet with an aesthetic visual. It can also be integrated into IoT and electronic devices and various smart gadgets in your daily life. The integration opportunities for DSSC are endless. DSSC, a device that charges with light, not only better for you, but also for the environment.
Perkenalkan, nama saya Sorel Mono dan saya salah satu peserta riset asisten di sini. Dan yang saya sekarang meneliti nanti tentang sel surya. Kita sama jalan. Jadi sel surya, karena kita hidup di negara yang lebih tropis yang memiliki matahari 12 jam, jadi kita harus meneliti mengenai sel surya atau device yang dapat menghasilkan energi listrik dari cahaya matahari. Nah, yang kebetulan untuk saya sendiri itu riset tentang material dari si sel surya tersebut, yaitu material perovskite yang tapi lebih spesifiknya itu menggunakan inorganic perovskite solar cell. Yuk, masuk lab biar tahu cara bikin solar cell.
Step pertama adalah untuk mengambil prekursor dari glove box dengan hati-hati karena prekursornya sangat rentan terhadap oksigen sehingga harus di-store di dalam glove box sehingga diambil. Nah, setelah diambil, step berikutnya adalah untuk mendeposisi prekursor kepada substrat sehingga menghasilkan lapisan-lapisan sel surya tersebut. Dideposisikan menggunakan spin coater. Untuk caranya adalah untuk meneteskan beberapa tetes dalam substrat kemudian di-spin sehingga menghasilkan sebuah lapisan tipis. Kemudian lapisan-lapisan berikutnya dideposisi dan juga dipanaskan di atas hot plate untuk membentuk film tipisnya. Step terakhir adalah mendeposisikan lapisan kontak, yaitu menggunakan karbon sehingga akhirnya terbentuk sel surya yang nanti akan diuji dengan menggunakan solar simulator.
Gimana kalian semua setelah melihat ini? Apakah tertarik mengikuti program Research Assistant? Jika tertarik, klik di bawah sini. Dan kalian bisa mendapatkan banyak ilmu dan pengalaman dari periset-periset di BRIN.
Kawasan Sains dan Teknologi Samaun Samadikun Bandung, sebuah pusat inovasi dan riset unggulan di Indonesia. Di sini masa depan ilmu pengetahuan dan teknologi dirancang dan dikembangkan melalui fasilitas mutakhir dan aktivitas riset yang beragam. Di kawasan ini terletak laboratorium riset terpadu kami, tempat di mana periset dari berbagai disiplin ilmu bekerja sama untuk memecahkan tantangan kompleks. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun dilengkapi peralatan canggih yang mendukung riset dalam bidang informasi, komunikasi dan teknologi cerdas, memperkuat sektor transportasi dan teknologi lainnya. Riset kecerdasan buatan, mekatronika dan elektronika di sini mendasari pengembangan teknologi masa depan, memungkinkan Indonesia bersaing dengan sistem artificial intelligence global. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun juga menjadi pusat riset kegempaan, pemetaan sesar, tsunami, gerakan tanah, serta kajian risiko dan resiliensi bencana untuk mengurangi dampak bencana geologis. Selain itu, riset iklim dan atmosfer yang dilakukan mendukung mitigasi bencana alam, pengelolaan lingkungan, dan pencapaian tujuan pembangunan berkelanjutan. Fasilitas pengujian untuk memastikan bahwa teknologi dan produk baru memenuhi standar kualitas dan keandalan yang tinggi. Di kawasan ini, tempat di mana ide-ide baru lahir. Kolaborasi antara periset, industri, dan mitra internasional menciptakan solusi inovatif yang berdampak luas. Selain itu, kawasan ini dilengkapi dengan coworking space yang dirancang untuk menciptakan lingkungan kerja yang produktif dan kolaboratif bagi sivitas BRIN dan para kolaborator. Fasilitas di kawasan ini telah memenuhi standar pelayanan publik, mencakup tempat ibadah, parkiran, dan toilet khusus disabilitas, tempat menyusui dan daycare, kafe, serta fasilitas kebugaran baik di luar maupun di dalam ruangan. Kami juga menyelenggarakan seminar, workshop, dan pelatihan untuk meningkatkan keterampilan para periset dan SDM pendukung riset, serta berbagi pengetahuan terbaru dengan masyarakat. Kawasan Sains dan Teknologi Samaun Samadikun Bandung adalah salah satu bentuk komitmen BRIN untuk memajukan ilmu pengetahuan dan teknologi di Indonesia. Dengan fasilitas modern dan aktivitas riset yang beragam, kami bertekad untuk menciptakan dampak positif melalui inovasi. Bergabunglah bersama kami dalam merancang masa depan yang lebih baik melalui riset dan teknologi. Kawasan Sains dan Teknologi Samaun Samadikun Bandung, di mana ilmu pengetahuan dan inovasi bertemu.
Research Center for Electronics is part of the Research Organization for Electronics and Informatics at BRIN. The Research Center for Electronics, or RCE, is home to 8 research groups that work together to explore new ideas, develop innovative tools, and contribute to national development through electronic science and technology. Advanced Photovoltaic and Functional Electronic Devices Research Group is one of the research groups in RCE, which specifically focus on the development of photovoltaic and functional electronic devices technology using novel semiconductor materials and the optimization of their fabrication process to obtain highly efficient devices. The objectives of this team are: 1. To bring together a multidisciplinary research team. 2. To be the center of excellence for research and innovation in the field of advanced photovoltaic and functional electronic devices technology. 3. To achieve a combined balance between high-quality science and practical technology as the main research output. This research group is located in KST Samaun Samadikun, Cisitu, Bandung, Indonesia, which is known to be the home of Advanced Semiconductor Device Fabrication Center. At BRIN KST Samaun Samadikun Bandung, a wide range of state-of-the-art photovoltaic device fabrication and characterization facilities are available to support the research and development activities. Together, we aim to build technologies that are not only advanced, but also meaningful and impactful. Electronics is a key area of science and technology that supports many aspects of modern life. In this research group, we believe that the development of advanced photovoltaic and functional electronic devices are essential as the building blocks for determining innovative electronics technology in the future. We also believe that collaboration is central to our work. Therefore, any future collaborations are always welcomed.
Dye-sensitized solar cell is one of the newest third-generation solar cell technology. Just like photosynthesis in plants, DSSC uses dye molecules to absorb light and then convert them into electricity through photoelectrochemistry. The key benefits of DSSC modules are clean and sustainable. The DSSC in this innovation runs on solar energy, which provides clean, endless power since it is the most abundant source of energy in the universe. So you will never run out of energy as you can charge anytime, anywhere, wherever there is light. Affordable. DSSC module uses much cheaper materials than the conventional crystalline silicon-based solar panels. DSSC can also be produced using simple processes in a typical lab without the need of high vacuum equipment. Flexibility. Unlike conventional PV, DSSC not only works under direct sunlight but also works under artificial light indoors and even on cloudy days. It can also be made in various sizes, colors, transparent, and even flexible. Integration. DSSC can be applied in building integrated PV, providing energy in smart buildings, yet with an aesthetic visual. It can also be integrated into IoT and electronic devices and various smart gadgets in your daily life. The integration opportunities for DSSC are endless. DSSC, a device that charges with light, not only better for you, but also for the environment.
Perkenalkan, nama saya Sorel Mono dan saya salah satu peserta research assistant di sini. Dan yang saya sekarang meneliti nanti tentang sel surya. Kita sebut jalan. Jadi sel surya, karena kita hidup di negara yang lebih tropis yang memiliki matahari 12 jam, jadi kita harus meneliti mengenai sel surya atau device yang dapat menghasilkan energi listrik dari cahaya matahari. Nah, yang kebetulan untuk saya sendiri itu riset tentang material dari si sel surya tersebut, yaitu material perovskite yang tapi lebih spesifiknya itu menggunakan inorganic perovskite solar cell. Yuk, aku biar tahu cara bikin solar cell.
Step pertama adalah untuk mengambil prekursor dari glove box dengan hati-hati karena prekursornya sangat rentan terhadap oksigen sehingga harus di store di dalam glove box sehingga diambil. Nah, setelah diambil, step berikutnya adalah untuk mendeposisi prekursor kepada substrat sehingga menghasilkan lapisan-lapisan sel surya tersebut. Dideposisikan menggunakan spin coater. Untuk caranya adalah untuk meneteskan beberapa tetes dalam substrat kemudian di-spin sehingga menghasilkan sebuah lapisan tipis. Kemudian lapisan-lapisan berikutnya dideposisi dan juga dipanaskan di atas hot plate untuk membentuk film tipisnya. Step terakhir adalah mendeposisikan lapisan kontak, yaitu menggunakan karbon sehingga akhirnya terbentuk sel surya yang nanti akan diuji dengan menggunakan solar simulator.
Gimana kalian semua setelah melihat?
Hello, Dr. Vipin Raj. Can you open your mic just to check if the audio is all right? Okay, we can hear you. May you share your screen just to try if it also works?
Yeah, sure. Able to see? Hi, Bunny. Are you able to see the screen?
Yes. Okay. Now perfect. It works. Okay. We'll start in 2 minutes.
Okay.
Okay. Thank you.
I was just trying to set this background, but
Mhm.
Are you still able to see the screen? I can't hear you.
Hi, yeah, Dr. Vipin Raj. We will open the session now. Maybe you can stop sharing first, just
Okay.
to give some intro.
Yeah. Yep.
Okay. Good afternoon, everyone. Participants of the second symposium on advanced photovoltaics. It's a pleasure to resume our session after the lunch break here in Indonesia. We are glad to have Dr. Bipin Raj from Nanyang Technological University. He is I will introduce him briefly. He obtained his PhD from IIT Bombay with a joint program with NTU. After his PhD, he conducted research at Tampere University, Finland, and then returned to NTU as a research fellow. He's an expert in lead-free halide perovskite material uh, especially for indoor PV application. At the moment, he is also working on LED and other optoelectronics application. So, hi, Dr. Bipin Raj, how are you?
Oh, I'm fine. Thank you, Ben.
I think if you may, I think we have about 35 minutes for presentation, and we will to be followed by Q&A. So the screen is yours.
Great. Thank you, Benny. Thank you, Maria, for inviting me for this session and organizing this. So I'll just share my screen. So is my screen visible? Yeah. Okay. So let's start. So I'll be presenting in brief about lead-free perovskites and why there's a need for lead-free perovskite and what is the road ahead with this. I've been working. So before I start about lead-free perovskite, I'll just show a brief. For some reasons, so I'll just show in brief about my journey. I started my bachelor's in electronics and communication from Mumbai University. And then I moved to Energy Center, Manit Bhopal, which is in India. So this is an institute which has the first dedicated energy center for renewable energy research. Here we had a lot of projects going on in solar cells, in wind energy, in small hydro projects, and all other energy technologies which were related to renewable energy and sustainable energy. So when I was here, I had two choices, either to go with wind energy or solar energy. So if you ask all my friends, they would let you know that I was so much passionate about solar energy that I decided to go with solar energy. But the fact is, because my background was electronics, I had no idea about wind turbines. So I just accidentally chose solar energy, which I don't regret today. But yeah, that is the reason why I went into solar energy research. And while I was doing my master's, I got a scholarship, which is from Department of Science and Technology, Government of India, and which helped me to pursue PhD from IIT Bombay. So when I moved to IIT Bombay, my research interest was basically Dyson-sized solar cells. And Professor Ashwini Yella was working there on Dyson-sized solar cells. But after I joined her, I realized that she had moved on from Dyson-sized solar cell long back, because she was the world record holder for the efficiencies in Dyson-sized solar cells. But then she decided that it's better to pursue research in perovskites rather than in Dyson-sized solar cells. That is how I started working on perovskites. And during my PhD, I got an opportunity to convert it into a joint program where I was able to work with Professor Nipan Matthews in NTU. And I worked on lead-free perovskite-inspired materials. Then I moved for my first postdoc to Finland, Tampere University, which is like very extreme climates, but was really good for solar cells research. And again, here I was working on perovskite-inspired materials for indoor photovoltaic applications, which I'll be showing you like in a couple of slides. Then right now I'm back to NTU and I'm working on inorganic materials, which is cesium lead bromide. It has a bit of lead in it, but yeah, right now I'm working on the method of developing large scale solar cells and also light emitting diodes. So right now I'm in a transition phase where I'll be moving from NTU to Lille in France. So again in Lille, I'll be working on lead-free perovskites for multiple applications, but here I'll be trying to understand the interface and the degradation studies at the interface using solid-state NMR. Okay, so during my research, I have been working on solar cells, light emitting diodes, photodetectors, indoor photovoltaics, then also process engineering, which means I also worked on some methods instead of working on the materials as such. So this methods was to develop the materials in a way to be applicable in the commercial for the commercial part of it. So trying to make an industrially viable process by which we can develop perovskites and perovskite inspired materials. I've also briefly worked on the stability of these materials. So before I move on to explain what is perovskite and try to understand what is the perovskite inspired materials, let me just give you a background about the way the solar cell technology is developing. So if you go through the NREL solar cell efficiency chart, you'll see that silicon solar cells is around just a second, is around like 27% in efficiency wise. But a major advantage with silicon is like it's highly stable. It can last for like 25 years without much drop in efficiency. But if you see why we are working on perovskites is, if you have a look at all the emerging PV technologies, like organic photovoltaics or CIGAs or the other technologies which are around, which is still in the research phase and not commercialized yet. So I'm not even comparing with silicon at this point. The efficiencies of perovskite have increased from it started in around 2010 and it has increased to around 27% so far, which is almost like beating silicon in efficiencies. But there are other factors which we need to work on before we can actually move on to a commercial product. Yeah, so a brief history about the perovskites and how they were developed. So the word perovskite comes from the structure which is attained by this salt called calcium titanate, CaTiO3. So this was discovered by Dr. Rose, who named it after Perovsky. So Perovsky was a mineralogist and he was a popular figure in those days. And it was a convention to name a new material or anything that was newly discovered. It was a convention to name by someone who is popular in that area. So that is why it was named as perovskites. But there are different stories which says that he was a mentor and all. But the true story is that it was just a convention because of which calcium titanate or all the materials which show similar structure were started to be called as perovskites. So one important point to understand here is that by definition itself, perovskite is a structure and it's not the name of a particular material. It just says that any material which can take similar structure to calcium titanate will be called perovskites. In 2009 was the first time when perovskites was applied in solar cells. So before that, there was all oxides. In 2009, Miyasaka came up with CH3 and S3PBr3, or in short, MAPBBr3 and MAPBI3, which was used as dyes in dye-sensitized solar cells. So I also have one slide regarding this. So I'll be explaining what is the difference basically. But in those days, it was dye-sensitized solar cell which was popular, and it had a dye which was used as an absorber. So this absorber material or the dye was replaced by MAPBI3 by Miyasaka. So his idea was to find alternatives to the dyes. But it was not a solid state solar cell. It had a liquid electrolyte. It was Dr. Park, who first started the idea of perovskite solar cells, where he introduced a solid state electrolyte into dye-sensitized solar cells. And at the same time, there was a group, Henry Snaith's group, which introduced perovskite not as a dye, because Miyasaka was using it as a dye. So he introduced it as a separate layer on top of the whole the electron transporting material, which is TiO2. And then this is how the journey of perovskite actually started. So if you want to really credit it to, we can say that it's Henry Snaith who actually made the current perovskite, the perovskite architecture which we are currently following in research. And then the other materials which are following the same architecture that he has introduced. So as I said, by definition, perovskite is a structure. This is how the structure looks. It is ABX3, where A is a large cation, B is a small cation, and X is halide in perovskite solar cells case, but it can also be oxide, by the origins of it can also be oxide. So, and if you see, this is the architecture. where you have a bottom contact and then an electron transport layer. On top of the electron transport layer, which is usually TiO2, we have like different architectures in which people follow compact TiO2 or mesoporous TiO2. On top of this, we have the perovskite layer, which acts as the absorber. Then we have the whole transport layer, which is usually Spiro or PTA. And then we have a top contact, which is usually gold or silver, depending on what kind of architecture you follow. So yeah, so this absorber layer is something that we are talking about when we talk about perovskites. Yeah, so every material comes with its own pros and cons. First, we'll go through the the pros. So the advantages of perovskite is that they have high absorption coefficient, and I would say that this is the most important advantage, which actually adds to all the other advantages that it has, because it has such a high absorption coefficient. They can be made into very thin films without breaking. So and also, whenever you talk about solar cells, there are two factors which come into picture. One is the absorption coefficient, and the other is the carrier lifetime. So it's always a trade-off between the thickness that you can go for and how thin or thick the film can be. If the absorption coefficient is low, you need to have very thick films to absorb sunlight or absorb a sufficient amount of photons, as is the case in silicon. And because the absorption coefficient is very low for silicons, we have to make very thick films with silicon, and that is why they don't have flexible applications. And the carrier lifetime in perovskites is larger in the sense it's relatively large as compared to the absorption coefficient that it has. So because of this, you can have very thin films but still have very good output from the material. That is why they have really good efficiencies. They beat silicon solar cells in efficiencies, but then there are other factors which are affecting their progress. Again, they are low cost, scalable, because compared to silicon, perovskites can be easily developed in a lab, and that is another reason why there are so many people working on perovskites, and there is so much of research focus on perovskites, because it's easy to set up a lab for perovskite research as compared to silicon solar cell research. Most of the silicon solar cell research goes on because people import the solar cells and then try to modify them. But in perovskite, you can start from scratch and make the device in your lab itself. So that is why, yeah, they have the scalability and like the low cost factor, which is adding to the performance of perovskite solar cells. And they have high performance, as I mentioned multiple times, that they are reaching efficiency of like 27%, which is much higher than silicon solar cells. And they can be used in tandem with the silicon solar cells. So what do you mean by using in tandem is like, because they have slightly wider band gap as compared to silicon, they can be coated on top of silicon and can be used to absorb some part of sunlight, allowing the remaining part of the sunlight to pass through, which can be absorbed by silicon solar cells. And so the overall efficiencies can go up to like 33% when you have a tandem perovskite solar cell working with silicon. Also, perovskites have now become a family of materials which can be used in different applications, not only solar cells. So they can be used in LEDs, they can be used in photodetectors, and now we also have the multi-quantum well applications where we can get the quantized emission from the material. So these are the pros. But as researchers, what we are interested in is the cons, because these are something which gives us the room to work on this and to improve. So I would say that the cons are the most important part as a researcher to look at. One issue with perovskite is the stability. So these don't have a life of more than, like, the best perovskite so far has a life of maybe 2 years, not more than that. While, as I said, silicon has a lifespan of like 25 years. So it's very difficult in terms of stability to compete with silicon. A major concern around perovskite is toxicity, because the most established, or the material that gives you 27% efficiency has lead in it, and without the lead, the efficiencies fall to like 1 or 2%. So the presence of lead makes it very makes it very difficult for them to commercialize it, because once you have the material in the solar cells and then the solar cells come into the market, then you are actually contaminating the environment. So the lead being there is a major concern. Once this is sorted out, the other things can be slowly sorted out, and that is the reason why we are working on perovskite inspired materials. Scalability so far is a challenge, because the high efficient devices that we have is actually made in the lab scale by spin coating methods. And spin coating is something like we have one substrate at a time, and we coat them using a spin coater which runs on a centrifugal force wala principle, which is not scalable. You cannot make large scale devices or modules using this. So scalability challenges are still there, which we need to work on. And there are other things like interface defects, because this has this multiple layers as compared to silicon, which has just one element there. So when you have these multiple layers which have to work together, the defects at the interface can introduce traps, which leads to losses in currents. So this is something that as researchers we can look at and we can work on. So all my research has been around toxicity and scalability challenges. So which I'll be showing in a short while. Firstly, why I'll just put in here why lead toxicity is a major concern, because lead is something which can affect all parts of your body, including your heart and brain. So in most of the countries, these are like in most of the European countries, you're not even allowed to set up a industry which has this much amount of lead, because if you are thinking about a solar cell manufacturing unit with lead in it, it won't, like, you won't get the license anywhere in most of the countries. So it is very difficult to set up a manufacturing plant with perovskite solar cells having lead in it. So it is important that we try to find out alternatives which do not have lead. There are always discussions around this, that it is there are other materials which are in the market, like cadmium telluride, which has cadmium in it, which is also toxic. But then it is not the same, because lead is highly water soluble. If you also see the norms in Singapore, if you're working with materials like cadmium or some other toxic materials, you need to do SME every year. But for lead specifically, you have to do it every 6 months, because it's highly water soluble and it can dissolve in the moisture in your body, and it can get into your body very easily. So it is not the same as the other toxic materials that are available in commercial products. Then we also have people comparing it with lead acid batteries, that okay, there are vehicles which use lead acid batteries, so why not use lead-based solar cells? But here the difference is, like, these lead acid batteries are always concealed inside a vehicle, and you don't get exposed. But if you have it in solar cells, you will be putting it in on top of the roof or somewhere in the open environment where rains can affect them and the material can get dissolved and get into the environment quite easily. Also, if you talk about the lead-based applications that are there in batteries and all, people are now moving away from it. We are coming up with lithium-ion batteries and trying to find out an alternative to it already, because we know it's a problem. So when we are coming up with a new technology, we cannot directly enter the market with a existing problem with it. So that is why we need to find alternatives. It's also about the workforce safety. When we set up an industry, we cannot have, so in the application point of view, maybe we don't get exposed to the material that much, but then there are workers who are working behind it. They need to fabricate the solar cells. So if they are made to do the mining of lead and then assemble the materials, then it is something that is not good for their life. So we don't want to risk their lives for our convenience. So these are some reasons why it's very important that we go away from lead and start to find some alternatives. Yeah, so coming to lead-free perovskites. Now, perovskite has become like a family name. So as I said, by definition itself, perovskite is ABX3. But when we move to lead-free, there are many different structures that are forming here. So all these numbers like 216, 113 is just like, so for example, 216 means A2, B, X6, which is like tin-based perovskites. Similarly, we have the double perovskites with silver, bismuth, antimony variants, and like a lot of these elements like copper, germanium, antimony, silver, tin, bismuth, all can be used. There are many materials in the periodic table which can potentially replace lead. All these materials have been experimented, but that is why I have a question mark here, that is it really perovskites? Because by definition, these materials are not perovskite, because they don't take the same structure as perovskites. But because they have some commonalities with respect to the kind of studies that are being conducted or the kind of architecture in devices they are being following, they are classified as perovskites. So we call them lead-free perovskites. As I said, like it's kind of become a family name, that because perovskites have become so popular that every new material that a person introduces, they want to put it into the perovskite category. But by definition, they are not perovskites. So there are some researchers who came up with a more accurate term, that is perovskite inspired materials. So instead of calling them lead-free perovskites, they started calling them perovskite inspired materials. So if you see the history, perovskite itself is like inspired from dye-sensitized solar cells. They follow the same architecture as dye-sensitized solar cells. In dye-sensitized solar cells, you had a similar transparent conductor on top of which you had TiO2 mesoporous layer. And then this was dipped into a dye which acted as the absorber, and then you had a liquid electrolyte which was a redox, which act as a redox agent, which helped in the oxidation reduction process to complete the charge transfer process. Then there came the solid state dye-sensitized solar cell, in which the liquid electrolyte was replaced with a solid material so that the stability was improved. And then later on, as I said, Miyasaka came up with this idea of having, the Henry Schneith came up with this idea of having perovskite as a separate layer. And then the mesoporous layer was also removed, and then we have the final architecture that we are following right now. Is used as an absorber in this final architecture is now defined as perovskite inspired materials. So before we go into look into some of the applications, I would just highlight what is the application philosophy of these materials, because there is no way we can compete with silicon. It is not even fair to compare silicon with perovskite. It is unfair on silicon to compare it with perovskites, because perovskite is a full family which has so many materials, but silicon is just a poor element which has just a few properties. So you cannot compare it with perovskites. But if you put silicon on one side and take one particular compound from perovskites and compare, then you will never have a perovskite which has all the properties of silicon. It can beat it in certain properties individually, but not as a whole. So what we say is, don't compare with or compete with silicons. The best thing is to go and collaborate with silicon, because as we do in research, we don't compete with the big shots in our area. We just go and collaborate with them so that we also get the mileage, and then we can come up with some good positive research. So that is the best way to go forward with perovskite inspired materials. We don't compare with or compete with silicon. We just go and collaborate in the sense we can work in tandem devices, where the perovskite inspired materials can be the top layer which absorbs some part of the solar spectrum, and then allows the silicon to absorb the other layer, other part of the solar spectrum, giving us much higher efficiency than what it would give if we are working independently. Then the other thing is, we just add value to the research. So silicon cannot be used in smart windows or displays because they cannot be transparent, but perovskites can be used in those. So we try to find out applications where silicons cannot be applied, and we try to find our solutions where perovskites can be applied. So this is how we try to find a research gap or a vacuum where silicon cannot be used. So we are not trying to compete with silicon. We are just trying to find places where it can be applied. And then don't try to live longer, but be relevant and meaningful. So what this means is, a silicon which has a 25 years lifespan can never be beaten by perovskites. So what we try is, we try to find applications which don't need you to survive for 25 years. You think about a mobile phone, which a new model mobile phone that you buy today, you won't be using it after 2 years. So, or 2 or 3 years. So why do you want a solar cell to power it for like 25 years? So just work on solar cells that can power some applications which don't require 25 years or 30 years. We'll just try to improve the stability to up to 2 and 3 years, so that particular applications can be taken care of. Another aspect is like staying away from what affects you. So basically, perovskites are affected by moisture and oxygen. So there is a good potential to use perovskite in space. So we take this material to space and make solar cells that can work in space where you don't have the moisture or oxygen that can degrade your material. So there are always alternative methods or alternative solutions, different solutions to it. We don't need to really stay on Earth and compete with the other technologies. And in the research phase, more than silicon is the perovskite inspired materials that should be of interest to us, because they have the potential to develop more. They are still in the early stages where a lot of improvement is required. So that is the philosophy of applications that we look for. And these are some of the work now that I've been working with in perovskite inspired materials. I have done some solar cell applications in which I'm working on copper silver bismuth iodide materials. This is called CABI. And this is also a double perovskite. The efficiency that I got for the reference materials was like around 1.2%, which improved to around 2% after introducing a little bit of bromine. So I'm not putting the efficiency numbers or highlighting the efficiency numbers that much, because these numbers are very low as compared to the silicon or the 27% of perovskite itself. But when I'm looking for lead-free materials, I'm not thinking about the efficiencies. What I'm thinking about is going step by step, where I make an improvement from the current state of the art and try to develop it into a better, get better numbers from now, so that other researchers can take it forward. So yeah, We also tried some interlayers. One of my PhDs who was working with me or whom I was mentoring, he tried doing some interlayers of cesium iodide in silver bismuth iodide materials. And then he saw that the efficiency was jumping from like around 1.2%, 1.3% to around 2.5%. So this is a huge jump. Percentage wise, it looks lower, but yeah, the total improvement is high. Another interesting thing is like when I joined for my postdoc in Tampere University, I started working on the indoor photovoltaics. So this is an alternate application of perovskite inspired materials that we can look for, because for indoor applications, as opposed to the conventional solar cell applications, we require a wide bandgap material. So in conventional solar cells, we require a bandgap of around 1.6, but for indoor applications, the ideal bandgap is around 2. So which is very nice when we see the lead-free aspects. So all the lead-free materials or most of the perovskite inspired materials have a band gap of around 2. So they can be used in indoor photovoltaic applications. So under the one sun, we get efficiencies of around 1.5 or 1.2. But when we use it under the indoor light, we get efficiency of around 10%. So if you see the numbers look very like huge, 10%, but they are not a true indication of the material. The thing is like when you measure the devices under indoor light, your input power is very low. That is why you're getting this high efficiencies. So if you see for the MAPI devices, the conventional triple cation solar cells, perovskite solar cells that give you 27% under one sun will give you like 40% under indoor. So we can use these devices in the indoor environment where your stray light can be used to power the devices, and it can be kind of applied in some clocks or calculators which require very low amount of power. So this is how we look for alternative application. In this case, the lead-free concept or the low toxicity concept becomes more important because you will be directly exposed to the system that you're using. Yeah, so we also look for some alternative applications like photo detectors, which is becoming popular these days. Perovskites are being used for photo detectors because of their the faster response and easy detectability. We have also tried improving the processes of developing the material by adding some tin into silver bismuth iodide. Here, by adding tin in the grain boundaries, we are able to improve the efficiencies by like 1%, and it also improved the charge transfer in the material. So these are some of the methods by which we try to improve the efficiencies of lead-free perovskites. There's still a long way to go, but yeah, this is like stepwise improvement in their performances. As I said, I also worked on some methods in which I try to develop the lead-free perovskite inspired materials by thermal evaporation. This was a modification to the conventional method that is followed in thermal evaporation. What I did is I evaporated silver and bismuth metals instead of evaporating the silver iodide or bismuth iodide metals because silver and bismuth are easy to evaporate, and then they form highly uniform films like you can see here. And then when exposed to iodine, they get converted into silver iodide and bismuth iodide respectively, which can be combined to form silver bismuth iodide easily. So these are some of my research that I've been doing on perovskite inspired materials. And there are other people also working on space applications and membristors. So my PhD supervisor, Professor Nirpan Matthews, is recently working a lot on this application of perovskites as membristors. This is because the forward and reverse currents are giving you different states in perovskites, which can be used as memories. And this has a large scale like industrial application as well. So this was something about the background research. So as a road ahead, I would say that we need to work on the materials in terms of not to compete with silicon, but to improve in areas where silicon cannot be applied. And in terms of methods, we need to, because we are still in the research phase, so we develop methods which can directly be applicable in the commercial phase. So as soon as we get a very promising material and we want to set up a company, we need to have the methods which can be used practically rather than having spin coating methods which cannot be applied like in a large scale. So yeah, that's all about what I had to say today. So if you have any doubts or you need to ask something, you can ask. Also, you can contact me through my email ID. I have put 2 email IDs here because, as I said, I'm in a transition phase and I'll be moving to another university. So I might not have access to the first email ID after a few days. So yeah, thank you.
Okay. Thank you very much, Bipin Raj, for the sharing your research result as well as your thought on the road ahead for lead inspired perovskite inspired materials. I think before we open to the Q&A, I have a personal question about when we shift from lead, we will use bismuth, silver, and other material. Do you consider also about if those material or those elements are earth abundant like lead, or
Yeah.
are we introducing a new issue like a material scarcity?
Yes. So there is always a trade-off. I would not say that all those materials are earth abundant, but they are fairly abundant enough to make like bismuth and sulfur. People are also making bismuth iodosulfide, like I showed you bismuth iodosulfide. So the halides are not all of them, like iodide is not that abundant. So if we move on to bromides, maybe it is a bit more abundant. And then we have bismuth, which is abundant. We have sulfur, which is abundant. So we can try to make materials which are non-toxic, but maybe slightly less abundant than lead. But then there is always a trade-off. The thing is, if you make a material which is properly which is very good, which has a very good performance, which can say for example, we make a material which is stable for like 10 years, and it has lead. You cannot set up an industry because most of the countries will not give you a license to set up an industry. So there is no point in working on a material which is earth abundant or what do you say? It's highly like gives you high performance, but then it cannot be commercially applicable. So that is why it is. Or there is always a trade-off, and we try to choose a method which will like choose a material which will give us more commercially applicable solution. The other thing is, though these materials are right now in like not that, if you look at the performances, they are not that great, but with time it will improve. So even the lead base took some years to come to this state, because when they started it was around 3%, and now they are at 27%. So with time, even silicon took some time to achieve this performance. So with time it will all come. So we need to work in a direction that after we develop everything, we should not be stuck because of the toxicity of lead. So we start the development phase in a way that we avoid the complications in future. Yeah.
Okay, thank you for the response. We have a few questions in the chat box. I think I will read them for you. The first one, in your opinion, what are the potential application more suitable for tin-based perovskite? Because tin-based is also less stable.
Yeah.
So do you have any idea about the future application for this family of materials?
Yeah, as I already said, though my expertise is not in tin based, I know that it is like highly unstable. But people are working on the stability of tin as well, and they are able to improve the stability step by step. It will always take time. But that is what I said. We are not trying to make a material that is stable for like 10 years or 15 years. Just think about an application like you have a watch that you'll be using for maybe 2 years. Why do you need a solar panel to like a solar cell to power that device for more than 10 years or 15 years? Because you will be anyways throwing that and changing to another watch maybe in a couple of years. So try to work out on applications where you don't need stability for long. Of course, the stability is much like it's very less now, and it's not even applicable for 1 year. So it is improving, but the target shouldn't be like 25 years. The target is to like improve it to a applicable point where you can apply it in small devices which can be used for short term.
All right. Yeah, you mentioned in your slide about this finding your own proposition and make the case for duration of the lifetime of the application itself. The next question from Dr. Firdaus. You've been working also with bismuth perovskite, and as we know that tin base is very strict in terms of oxygen level. As for the bismuth-based perovskite, do we also need to have such a strict control environment? And the second question is, what's your opinion whether if about the lead-free, would it be competitive in the future in terms of efficiency?
Yeah. So for the first question, I would say that all the lead-free materials that I've been working, the bismuth-based materials that I've been working on, it it can be made both inside the glove box and outside the glove box. And the funny part is, if you make, like every time I made it inside the glove box, I got lower efficiencies. The reason for this is bismuth iodide tends to form bismuth oxyiodide, a thin layer of bismuth oxyiodide on top of the perovskite, which actually helps in the performance of the solar cells. So if you try to make it in a controlled environment inside the glove box, you might end up having lower efficiencies. So I would say bismuth-based materials are better to be made in the ambient atmosphere as compared to what you do it in the like for the conventional perovskite inside the glove box. And for second, sorry, can you just remind me of the second question?
In the future, do you think the lead-free will be good enough in terms of efficiency?
Yeah, I have already put this in the presentation. What I was trying to say is we don't want the lead-free materials to compete with any other kind of solar technology. So we are just trying in a way to find applications of its own. So as I said, like the short-term applications or somewhere in space where you don't have oxygen or water to destabilize the system, or somewhere in indoor applications where you need very low power, you don't care about the efficiencies that much. So these kind of applications you can always look for. So it's not that you need to compete with silicon in all. Since I am with my experience in lead-free perovskite solar cells, I'm saying that at least in near future it cannot compete with silicon, because silicon is much more established and it has really good performances. Even the stability that we talk about 25 years, it's not that after 25 years silicon cell cannot perform anymore. It's just that the efficiencies drop a bit. It goes up to like 17%. If it is from 26%, it goes to 17%, but it still performs. But a perovskite solar cell cannot perform. Maybe even after a week, it cannot give you anything. So yeah, so when you enter research into perovskite, you don't try to compete with silicon. What we say is, like, let's try to find out alternative applications where you don't need that much of stability.
All right. We have Wilman raising hand. I think you can unmute and just say your question.
Okay, thank you, Dr. Vivin Raj. I have two questions. So I'm also interested on the lead-free perovskite. So I'm interested on the CABI system, CABI. So how did you make this one? So you mentioned that for your silver bismuth, you did thermal evaporator, but how about this copper base? And the second one is, I see the band gap is quite wide, right? I see the onset is around 700 something.
Yeah.
So to match with the indoor, it seems we need to widen the band gap a bit. If we see the response of the LED. So how we can do that in here? Is it the same as simple as replacing the iodine with bromide, or do we need other strategy in this case for this lead-free system? Okay, thank you.
The band gap tuning. So when you talk about indoor system, sorry, I'm going to the second question.
Yeah, indoor system. Yeah, correct. Indoor.
So when you talk about the indoor system, you don't do anything differently with the materials. The material aspect is exactly the same. It's about the characterization. So instead of measuring your devices under one sunlight, you are measuring it under a standard indoor spectrum, which is 1000 lux. But the indoor spectrum itself has much lower. If you can see the spectrum once again, can you still see my screen? Is it still?
Do you mind to share again your presentation?
Yeah, if you see the spectrum is different. This is the indoor spectrum under which the measurement is done. So the material aspect remains the same. So the band gap tuning, everything is similar to what you do with the conventional way, because the material is not changing. It's only how you characterize them that changes. That is why I said that the efficiency of 10% that you see, it's not very exciting because if you take the conventional MAPI devices, the triple cation devices, and measure under the indoor, you will get like 40% efficiency. So it's only the power of the spectrum is much lower. So you see higher numbers, but then this power that you get from the devices in the indoor is enough to power some indoor devices. That is the whole idea.
It's matched very well.
Sorry?
So it's matched very well. The onset with the profile of the LED.
Yeah.
The onset around 700.
Yeah. So this is like for Kabi, the band gap is around 1.9, and for the indoor to be like, if you see the from the calculations, the best band gap for once an application is like 1.6, and for indoor applications is like 1.9, and Kabi is very close to it. So if you see that we have a lot of work on copper silver bismuth iodide in indoor applications within the group, like we had in 1 year, we had like 7-8 publications on same material just by making minor modifications.
Okay, thank you. So the first question is, how did you
Sorry,
make this
I forgot
this Kabi?
Sorry?
How did you make
Yeah,
this Kabi?
that was synthesized by simple solution process.
Oh.
And it was also done outside the glow box. So all the lead-free materials that I've been working on was done outside the glow box.
Okay, thank you.
Okay. Following up the question about the indoor PV, your material has a band gap around 1.9.
Yeah.
But in the VOC, you only see about 1.6, 0.6 or 0.7. Could
Yeah.
you elaborate the reason for this huge voltage loss?
Yeah, so this is true with almost all perovskite inspired materials. If you take even the most established copper cesium silver bismuth bromide double perovskite, it has a band gap of around 2.3, but the VOC that it gives you is 1.1. This is because these systems are like vacancy order systems, or they are like more defective system compared to the MAPI system. That's why the VOC is always much lower than the expected values if you compare with the band gap. And Kabi is like a vacancy ordered system. If you see the structure, it is not a continuous structure. You will have vacancies in between. So it is even more defective system. So you have a lot of VOC losses.
Okay, I think it has answered Julia's question. The next question, we mentioned about lead toxicity, and Dr. Maria Ulfa also is wondering how about the solvents, since that the toxicity concern is not only on the materials, on the perovskite material. What's your thought on this solvent toxicity?
Yeah, so that's a good point. For all the copper silver bismuth based or silver bismuth iodide, it's 50% DMSO, 50% DMF when we do the solution process. And I agree to that point that the solvent is also not a green solvent. So there is toxicity of the solvent. But then there is less possibility of you getting exposed to it in the application perspective. But anyways, I accept that it is a problem with lead free, that you are still not solving that problem of solvent toxicity. But then if you compare with the conventional perovskite, you are solving at least one problem. And if you go to the thermal evaporated methods, then there is no question about the solvents. Because if you are moving to a large scale or a scalable process where you don't depend on the spin coating process, but you do a thermal evaporation, then you don't need to worry about the solvents. And that is why I said like the road ahead is that we also work on the methods in a way that when it comes out finally in the commercial stage, when you have a performing device, you don't have to think about how to change it from a solution process method to a scalable method. So when you already have a scalable method in thermal evaporation, the solvent issue is already sorted.
Okay. I think we still have time for question. If anyone wants to ask, you can raise hand or chat in the chat box. I think from me, earlier in the slides, you mentioned about lead is not the same in terms of toxicity because it's in ionic nature. So, but earlier, in like 2020 or before, I think one of the research paper mentioned that about bioavailability of lead ion are similar or maybe comparable to tin as well. And tin, in a way, is not so safe because it can also be absorbed by surface or over the body skin. Do you have any thought on this? How we should see toxicity with respect to any leakage to the environment?
Okay, so when it comes to discussion around toxicity, it is not about the toxicity of the material as such. It is about what happens when it gets into the environment. So tin getting into the environment, see, tin itself in itself is not stable. So when it gets into the environment, it might form tin oxide or some other material, which are not that toxic. But lead getting into an environment is like it forms compounds which are more toxic. And the other thing is, if you are exposed, what happens when you are exposed to tin and what happens when you are exposed to lead? Lead can easily get into your body. Tin cannot get in that easily into your body. That is what I said. Like, there are solar cells with cadmium in it. It's not that cadmium is not toxic. It's just that how your body responds to that, how easy it is for them to affect you, makes more like it affects in the policy making things. So that is why there are different policies about lead and different policies for tin. So, for example, if you have tin in your material and if you're working with tin, for example, in Singapore, if you're working in tin, you might have to do a SME or a medical checkup every year. But if you're working with lead, you have to do every 6 months. So this difference in policies itself is because of the way your body responds to these elements, not the material toxicity alone. So if you compare the toxicity of tin and lead, maybe you would say it's more or less the same. But then what happens when you get exposed is more important.
Okay. Okay. Yeah. I remember the study was on plants, on some vegetables. So probably it's gonna be different with human body.
Human body, yeah.
All right then. I think we can conclude this session. Thank you for all the participants for your intriguing questions on this, because lead-free are still relevant in when we talk about mass scale production. And once again, we'd like to thank Dr. Bipin Raj Sugatan for your time and your sharing. And next, we will move on to our next speaker. Oh yeah, let's make a virtual applause for Dr. Bipin Raj. Our next speaker is Associate Professor Luigi Vesse from University of Rome Tor Vergata. He obtained his doctoral degree from University of Rome Tor Vergata, and since then he's been a researcher at Center of Hybrids and Organic Solar Energy, Department of Electronic Engineering, University of Rome Tor Vergata. I think I'll just say hi first. Hi Luigi, how are you? It's early there in Italy.
Hello, thanks for the nice introduction. I'm fine, thank you very much.
Okay. Dr. Luigi will share with us about the
sure.
upscaling process, and the screen is yours.
Share my screen. Can you see my presentation?
Yes, can see your slides.
Okay, thank you very much. Okay, thanks for the nice introduction, and thank you for inviting me at this symposium. As the chair said, I am Luigi Vesce. I am assistant professor at the University of Rome Tor Vergata. I belong from 2-3 departments. I have some teaching duties at Department of Biomedicine and Prevention, and then I have my research activity at the Department of Electronic Engineering and the Department of Physics. Today I will talk about the thin-film perovskite photovoltaic technology, from lab cells to scalable printed modules. During my talk, I will introduce the research topics in my group. Then I will talk briefly about the perovskite solar cell technology, the scaling up from cells to module, and then our processes to print a device, a module and panel. The Center for Hybrid and Organic Solar Energy is located in the Tor Vergata University campus. Our main objectives are the printed electronics, the research and development on organic, dye-sensitized perovskite photovoltaics, and we are mainly involved in the device design and the scaling up of the devices. We in the past also did some technology transfer to industry, also by founding some spin-off startup, and so our main input is the photovoltaics, but this helps us also to work on different fields, as for example the energy storage, the printable thermoelectrics, the light efficiency, and so in this way we can find new applications, architectures, processes, testing new materials, and so on. So the perovskite for PV technology is mainly formed by an organic and inorganic cation, like the methylammonium or formamidinium or cesium or a mixture of this. And then there is a divalent metal as lead and an inorganic allied anion. The typical NIP mesoporous structure is composed by an electron transport layer, and then this serves to suppress the shunting paths. And then we have a mesoporous oxide layer that is filled with highly crystalline perovskite absorber. And then we have an old transporting layer. At top of the stack, we have the counter electrode that typically is a metal, but we will see during the presentation that we can substitute this with other material, less costly and also more stable. The working mechanism is really simple. So when the light hits the device, there are an exciton photo generation and dissociation, and so we have a selective injection at the HTM and ETM interfaces, thanks to the band positioning of these two layers. Finally, we have the injection at the positive and negative contacts. The perovskite solar cell technology has some advantages. Here I summarize some of these. So we have an high absorption coefficient, a very low exciton binding energy. We can work on flexible devices. We can tune the band gap, so we can have transparent on opaque devices or devices that can work under indoor light, for example, for the energy harvesting. But the real exploitation at the market level of this technology can be feasible only if the small lab scale cell will scale up to module. There is a classification about the size of the device. So we have a lab scale cell if the size is less than 1 centimeter square. Then we can speak about a mini module if we have a size less than 200 centimeters square, then a sub-module if we have a size more than 200 centimeters square. This is a way to make a sort of clarity, because sometimes people claim very large area module with size more than 30 centimeters square and so on. But this is the classification according also to NRL. We talk about module. Module is an interconnection of different cells. In this architecture that you can see is a series interconnection. This means that before the deposition of the full stack, we realize by a laser a stripe on the FTO glass in order to insulate the different cells. Then after the deposition of the full stack, before the deposition of the counter electrode, we realize another laser process that the name is P2, so is to remove the full stack except the FTO, and then we have the P3 that is after the counter electrode in order to insulate the counter electrode and to avoid any short circuit. During this scaling up journey, we can have some issue that are related, for example, to the front contact sheet resistance, and this is why we have to use low sheet resistance substrate, and that's why I showed you this series connection of the cells, and so we have also to optimize the cell width in order to reduce the recombination. Then we have some issue related to the interconnection, so the interconnection resistance and the interconnection dead area, that is the part related to the P1, P2, and P3. So we have to narrow this area and to optimize the laser process, and then we have at the end the layer homogeneity that you have to face when you scale up to a big sites. And here you have to optimize the printing technique, the material composition, the deposition environment also is really important. So the perovskite solar cell scaling up face these three these three targets that are to obtain efficiency, to obtain stability, and to obtain a process that is at low cost. And one should try to achieve all of this. In one of our recent work, we focus on deposition techniques that you can use for the fabrication of a perovskite solar cell, and mainly from a life cycle assessment point of view. In the life cycle assessment, you can compare the eco profile of different things. In this case is the eco profile of different fabrication processes. Here is the blade coating outside the glove box, in the glove box, the spin coating, for example. And anyway, this work show once again that meniscus coating processes that can be blade coating or slot die coating has the lowest impact. And because they have a low electricity consumption and also low material wastage with respect to a spin coating technique. So in our work, in many of our work, we focus on this meniscus coating, box slot die or blade coating. In this work, you can see how we deposit the perovskite in the movie that is on the right side. So we first deposit the precursor solution of the lead iodide, and then we, by blade coating, assisted by air to preliminary dry the layer. Then we deposit the anti-solvent that helps us to remove the solvent, typically DMF, DMSO, that are in the perovskite solution, and start the nuclei formation, because all this process is optimized according to the Lamer model. So we start from a supersaturation state where you have the solvent evaporation and the precursor concentration starts to increase. Then you have burst nucleation, and the crystal growing when you have big grains and start to grow the film. But not only the perovskite, here all the stack except the counter electrode, but then I will show you how we substitute the gold counter electrode. So the full stack is deposited by blade coating in ambient environment. Here is the XRD peaks showing the alpha phase of the formalinium based perovskite that we choose for this work. Also the phenylethyl ammonium passivation peak. You can see that we used to reduce the recombination on top of the perovskite, and from the morphological image it's easy to see the large perovskite grain that can contribute to reduce the grain boundaries. Reducing the grain boundaries means to have less recombination, less site that can start some perovskite degradation, and also the mirror-like perovskite deposition. Here is the performance. So we got on 0.5 centimeter square an efficiency of 20.8%. And on 0.09 centimeter square, an efficiency of more than 23%, just to show you that how is the contribution of the scaling up. So where you are increasing the area, you have a little drop in the performance, mainly because of the fill factor. Okay, we have great performance deposited by blade coating in ambient air, but we have still an issue, that is the gold. The gold is an issue because it's costly, it's high costly, but also as we are confirmed by the life cycle assessment. In this work, we show the fabrication of a sub-module, so with the size that is more than 200 centimeters square. And in any case, both mini and sub-module, the highest contribution on the eco profile of the device is related to the gold evaporation, because of the material, because of the process that is thermal evaporation. So we decide to substitute the gold. We use the carbon counter electrode. So why going to this electrode? Because of the, as I already said, because of the metallic electrode main drawbacks that are related to cost, but also related to the stability of the device, because you have gold ions diffusion toward the perovskite, the oxidation of the metal. The gold has a low hydrophobicity, so it's not good for the stability. So we can substitute the gold, and in some cases also the HTL, with a carbon black graphite layer, treated so far at low temperature. This is good because we can easily integrate some HTL, because the process is almost the same. We are removing the gold and putting on the top the carbon. It seems easy, but you have to optimize the interface. But in principle, it's easy. You can still control the crystallization of the perovskite, because it's not the concept of the high temperature carbon where you have to infiltrate the perovskite after the deposition of the carbon. So here you can use flexible substrate because of the low temperature process. So you can use in case the roll-to-roll fast processing. So the carbon can help to reach the goal of to have efficiency cell, the stability, low cost, the sustainability of the full process. Okay, here is one of our attempt to use the carbon. In this work, we use an HTL-free cell, so means that we have not the HTL in the stack. Here we use this tetradecylammonium as 2D material that helps to improve the hydrophobicity and also can guarantee the defect passivation. We obtain the performance after optimizing all the process, the material, and so on. This is the first time that this material is deposited by meniscus coating, blade coating technique. We have a performance of maximum performance of 16.6%, and also almost some stability if you take into account that we have measured this after more than 500 hours. In another concept, we used an HTL here helped with another passivation layer, that is this xyl-3-methylammonium bromide, that helps to improve the interface between the perovskite and the P3HT. Here we got a performance more than 15.5%, with a voltage that is more than 1 volt. It is very good if you take into account a carbon cell. Then we continue to optimize the interface between the perovskite and the carbon layer. In this case, we use the last architecture related to the H-tab and the P3HT. And then on the top, we put the nickel oxide layer deposited by blade coating. Nickel oxide is generally used in the PIN architecture, that is the inverted structure, because it's more easy to disperse the nickel oxide in water, and so you can deposit this layer as a first layer before the perovskite. In this case, we optimize the solution of this material in a way that you can deposit basically on top of the perovskite, on top of other HTL. Each layer has its role. So the nickel oxide is a very good inorganic HTL, can be a buffer layer that protects the P3HT that can be corroded because of the carbon, because as you can see this in this picture, if the carbon stay for a long time on the perovskite layer, you can have some issue before the annealing of the carbon. And then by using these combined effects of enhancing the interfacial contact and reduce the trap density and the recombination losses, we got a performance of 16.3%. Then we check the stability, the durability of this cell. We encapsulate with an encapsulant that I will show you later, that's used also on the module. This test is an isocell 1. This means that we are testing at 40 degrees under light at the maximum power point. So in this case, the cell is working. And so we have a stability more than 1,000 hours. So you can see that we are above the 80% of the efficiency. In some cases, if the encapsulant is not well, I mean, deposited on top of the cell, you can have also some drop. You can have some drop in the performance. Okay, now it's time to scale up. To scale up, not gold cell as we did in some of our past work, but here today we would like to show you the scale up of the carbon cell. First, we scale up the perovskite. So we scale up on 11 by 11 centimeter square substrate. We check the XRD on different point of the layer to see if we have still the from a medium based perovskite is confirmed. Then we check the absorbance in different parts of the layer to see if the deposition is homogeneous. And then it's time to scale up and to realize the module. As I told you, we have the P1, P2, P3. The dead area width is the area from the P1 to the P3, and then we have the active area cell width that is this part that is in between the 1P3 and the P1. About the laser patterning, this is the most difficult step for about the P1, the 3 laser step, because here you have to remove the full stack, but not the FTO. Otherwise, you have not the interconnection between the different cells. To do this, we check first the depth of the etching. If the depth is comparable to the thickness of the full stack, this means that we have removed the full stack. Then we also check by microscope, a simple, for example, 3D microscope. We check if we have ruined the FTO. As you can see in the picture on your left, you can see that we have described, but we have also described the FTO, and this is not good. Here you have high sheet resistance and very high resistance. In an optimized step, we have a sheet resistance that is comparable with the bare FTO sheet resistance, that is about 7 ohm square. We are there, and the resistance that is 2 ohm, that is again comparable with the bare FTO. Then, thanks to SEM-EDX analysis, we see if in the P2 trench we remove the perovskite contribution. So we remove the lead, the iodine, for example, and this is the case. So you can see that in the P2 trench we removed all of this. There is a little part of tin that maybe is related to the tin that is in the FTO. And so it's good. Then, in order to predict the losses that we have in the scaling up, because the losses can be related to the deposition, can be related to the interconnection, we developed this model that is based on the transfer length method in order to have a proper estimation of the resistive losses. Here we divided the losses in 3 contributions. We have losses related to geometrical losses that are very simple. It's related to the W int is the width of the interconnection. W active is the width of the active layer, the active part. Then you have the contribution related to the TCO that is related to the conductive layer on top of the glass substrate. Here you can see the J and V at maximum power point of the cell, the sheet resistance of the TCO, and again the part related to the geometrical aspect. Then you have the losses related to the P2 trench. Here you have, apart from the other that you have already seen, so the related to cell, geometrical, and so on, we have the transfer length. The transfer length that is the square root of the resistance, of the contact resistance and the sheet resistance. And in this formula, you have also the width of the P2. After doing some calculation with this formula, we reach this graph. So in the first graph, you can see that it's easy to understand that when you increase the interconnection width, you are increasing the geometrical losses. About the TCO resistive loss, you can see that if you increase the active area width, you are increasing the losses in relationship with the TCO. That's why I said that we have to optimize the width of the single active area. Then we have the resistive losses related to the P2. Here, if you increase the P2 sites, you are decreasing the losses. since we take into account the losses of the related to the carbon interconnection, we need to use a P2 with about 500, 600, 700 nanometer till now with the carbon layer. About the P3, we used in some case the screen printing in order to have embedded in some case the P3 step, so we have not used the laser in this case. In the picture bottom left, you can see a snapshot of the three, the P1, the P2, P3 interconnection. The black layer is the carbon that is on top of the P2 in order to do the series connection as in this picture. Here are the performance. Here are the performance without the HTL, so in the HTL-free module. We got a performance of efficiency of 15.6%, so just about 6% losses with respect to a 0.5 centimeter square cell, with a very good VOC, taking into account that here you have 8.2 VOC because you have 8 cells. We have a series connection, so we have to sum the voltage of each cell, so we have more than 1 volt per cell. It's good. Then we try to have the very good efficiency in order to use the other stack with the PTST and nickel oxide, but also adding an anti-reflective coating on top of the glass FTO, and in order to help the conduction on top of the carbon layer, we have the silver layer, but the carbon still is acting as a counter electron. In this way, in this case, we got more than 17% efficiency. Again, the fill factor is very high, 67%, just 4% less with respect to the cell. And again, we confirmed the low losses that we have with respect to the cell. We then encapsulate the module. We encapsulate the module by using this polyisobutylene material. That is a material that we developed together with a company, with the addition of thermal conductive 2D hexagonal boron nitride that helps to improve the barrier, the barrier property of the encapsulant. In the past, in the very recent work, we demonstrated the stability according to ISO's D2 test. The ISO's D2 test is a thermal test at very end, so at 85 degree the VOC, and also according to L1. We optimized the process in this for this module. After this, we experimented no performance losses after the application of the of this material. Actually, we also used the same module for indoor. For example, for indoor application is not shown here because of the time, but we can use the same module also for the energy harvesting. To conclude my presentation, so I hope that I show you that the scaling up needs to optimize materials and process. The process should be reliable and with the potentially with the high throughput. We show the benefits from a technological LCA manufacturing point of view. The carbon can be a really valid alternative to the metal electrode. And as I already anticipated, we can use this device both for outdoor and indoor applications. I would like to acknowledge the people that are in my group, and also the European project Diamond and Sun24 that founded part of these results. Thanks for your attention. I'm open to any discussion, or if you want to reach me out through this contact. Thank you very much.
Thank you very much, Luigi. Very impressive. sharing about your experience in Rome, Italy. I think we will have about 10 minutes for Q&A. There are a few questions already in the chat box. I'll just start quickly from Professor Rahmat. This question is, how do you overcome pinhole formation when you make large area? And how do the perovskite layer thickness variation affect the perovskite solar module in terms of performance? Is the thickness critical?
Yes, okay. So about the pinholes, so the pinholes is very easy to see if you work in ambient environment, as in our case. Because in ambient environment, yes, we are controlling the humidity, but we have some, we work under 30% humidity. We have not some ppm as in the glow box. So this means that the pinholes can affect our layer. We control the pinholes thanks to the process and to the condition. So we saw that if the humidity is more than 40-50%, it's not easy to remove the pinholes. If you are at less than 20-30% humidity, you have still some pinholes. You can control this with the process thanks to respecting the Lamer model in the perovskite in the perovskite conversion. So we have this air assisted method that helps the perovskite to be quickly dried and so to be quickly formed. About the homogeneity of the thickness, this is very important. That's why we control the thickness of the layer, different parts of the module. So we control the thickness of the layer, the absorbance of the layer, the performance in different parts by fabricating cells in the full size of the module. This is very important to be controlled. We control this thanks to the blade coding method. But if then we would like to further scale up to a size that is more than the size that I show you, as in our previous work, there you have to use the slow die coating method, because with the blade coating at some point you have no more the material that can be deposited, because the blade coating can deposit just the material that you put at the beginning of the process. With the slow die coating method, you continually have a continuous filling of the material, and so you can have an homogeneous deposition. We are going to have an in situ characterization of the homogeneity of the layer. We cannot yet do, but in the near future we can do.
Yeah, I believe it's a long optimization in the processing for to get a very impressive efficiency. The next question from Widya: how is the effect of moisture to the VAPI formation? You mentioned about 30% RH, but so is it very sensitive? I just want to clarify that. Is there any working range in terms of the moisture level?
Yes, there is a working range. So the best would be if you have for example, your blade coating system or slow die coating system inside the glow box, okay, with the nitrogen environment and so on. But if you think about the scalability or the industrialization of the technology, this is not so feasible having such a big glow box that in a plant or in a company. So we saw that the range is about 20-30%. So less than 30% is mandatory to have a good perovskite layer. In any case, it's also important to have a passivation layer on top of the perovskite. This helps to maybe to cover some pinhole that you can have or to remove some defects. So this helps if you have defects in the perovskite, and for sure you have defects in any case, but more if you are working in the blade coating outside the glow box.
Okay. Want to ask question about the drying effect. The state of the art now is using the air knife as a way to crystallize. But that process generate solvent vapor. Would you think?
Kasih ide. Nah, nanti kita yang eksperimen kita lihat bagaimana possible nggak 1000.
Sorry. Do you think that the another alternative processing will be used in the future that produce less vapor, for example?
Yes, principally in the literature you can find 3-4 methods to deposit the perovskite with the blade coating. That is the gas quenching, as you mentioned. That is the vacuum quenching. That is just the thermal annealing, for example, or in our case we have the anti-solvent method. Anyway, the anti-solvent method, it seems to do not, you cannot industrialize, but take into account that you are not using so much material, and also so it is not so costly. About the vapor that you generate, for example, in our case, when you use the air knife, we have the extraction of the fume in the box, so we can extract the fume at the same time. In our case, our air knife is perpendicular to the layer, but I've seen in some work that people use, for example, an air knife that is at 45 degree, for example, and so you can easily remove the solvent. Or in other work, I've seen that someone has like so yeah, they have an air knife and also have some like a vacuum on the other side that can remove easily all the vapor. So it's something that you can manage in the process.
Okay, thank you for the answer. Next question from Maria Ulfa. Why do you choose FAPI over mixed cation perovskite? And do you have any insight on two-step FAPI deposition in ambient environment?
Okay, so the question is, why are you using FAPI?
Yeah, instead of mixed cation.
And not mixed cation. Okay, thank you. And the second one is
how about two-step deposition in ambient? Is it manageable?
Okay, thank you. Yes, okay. So about the first question, so we start to use the method that I've shown you with the triple cation perovskite. Then we used also for double cation, now for FAPI. FAPI now is the most attractive because you can get the highest efficiency now. So in principle, we choose to use the FAPI for this reason. Because it's the perovskite where we can get the highest performance. It's not so easy to control the phase because sometimes you can have the delta phase of the FAPI. That's why you have to characterize often with the XRD. But in our case, it seems that we have the alpha phase. Also, if it is not a pure alpha phase, because we add a bit of cesium in the formulation that helps in the deposition. Then about the two-step, it's possible to do. We are working on the deposition of the lead iodide, and then on the deposition of the salts. We have some work also by evaporating the lead iodide and depositing the salts by blade coating, and this is very good because in this way you are not managing the lead, you are not managing the solvent that are in the composition, so mainly the DMF, and so you are also not only managing very solvent as EPA and so on, that it are not so dangerous.
Yeah, I think having a two-step, you separate the DMF part.
Exactly.
Yeah. So I think we have last question from Wilman. So in ambient process, how do you manage to get RH 30% or below? And then and is that condition critical for perovskite only or as well as other layers?
Okay, this is a good question. So first one, we can manage this humidity because our blade coder, our system that can be also slot decoder, is inside the big box, and in this box we have a dryer that continuously guarantee the percentage of the humidity. Then about the second question, yes, it's important also for the other layer, the condition of the humidity and also of the temperature. You have to take into account also the temperature, because if you have high temperature, all the parameters of the process we are going to change. About the other layer, for example, we have seen that humidity is a problem for the spiral layer, and also for the passivation layer. So it's important that for all of these layers we take into account this. It's not easy always to have this condition, because if you decrease the humidity, sometimes the dryer can increase the temperature, for example, of the environment, and this is not good, because then you are changing completely all the parameter of the process, because you are using sometimes low boiling solvent. So this is something that can change.
Okay. I think I still have one curiosity about the laser, because it's rarely mentioned in the question session, because we talk about that area that we need to minimize. So are the laser setup something commercially available, or it's developed in-house?
No, it's commercially available, the laser. The laser, we start to use, you have to use a UV laser because of the wavelength that is good for the perovskite. And then now we are using a picosecond laser. Before we used a nanosecond laser, but it's something that you can find commercially. So with the nanosecond layers, the laser, the setup was completely built by ourselves. So we have the laser, then all the mirror and so on. With the picosecond laser, we bought one from a company, so it's easily.
I see. Very last question, if you have 1 minute. So in Europe, I remember they are very strict in terms of safety and toxicity issue. Is there any safety issue when you have your process, like regarding solvent or precursor materials? So far, how is it in your country about the regulation?
Sure. So if you take that, so if you are still in a research environment, university, the amount of the material is not so much. So, but if you think about a production line, the problem are the solvent, the DMF, for example. The DMF is a more toxic solvent that we have in all the layer, and there are some we have started some activity to remove the DMF and substitute with other solvent. For example, NMP is one of the solvent, or using a double step, as I already said, the double step method, so completely avoid. And about the lead, there are some research line working on the substitution of the lead iodide with the tin-based perovskite, for example, to remove the lead in the stock.
Okay, thank you very much. It's very insightful session with you, Dr. Luigi.
Thank you.
And your work also are very relevant in Indonesia here in our institution regarding upscaling efforts. And I think we will hope to maybe collaborate in the future with you and your group. And I think we can conclude this session. Thanks all the participants for your question and active involvement. I think as a chair, once again, I want to thank Dr. Luigi Vese and also previous speaker Vipin Raj Sugatan. I'll pass the mic to the MC for the closing. Thank you.
Okay, thank you very much, Pak Bening and Dr. Luigi, for the excellent session. Ladies and gentlemen, this concludes the program for day 1 of our symposium On behalf of organizing committee, I would like to sincerely thank all the speakers, chairs, and participants for your active participation. Please join us again tomorrow at 9 a.m. in the same room for day 2 of the symposium. Have a pleasant evening and see you tomorrow. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you.
Apakah tertarik mengikuti program Research Assistant? Jika tertarik, klik di bawah sini. Dan kalian bisa mendapatkan